Il y a un ou deux qui sont pas de oui, il ressemblait aussi à un peu. C'est un peu égal en termes de choix. Il nous a proposé un truc à moitié vers le voilà, ça fait un moitié. Une question, c'est un arbre négatif de l'achat. Oui, à l'achat. Ah ouais, c'est ça.
Ah ouais, putain, ce que c'est dit. Oui. Ouais. Okay. Ouais. Et moi, en fait, j'en
I can do time, but or whatever. Okay.
You're presenting today, so I can.
I'm presenting today. Before lunch, I can do whatever you prefer.
Yeah.
It's okay.
Donc tu montres au présentateur à peu près. Et après, c'est ça qu'on lui expliquer à chaque fois qu'il y a un nouveau chat. Et 10 minutes, j'arrêtais ou alors si vous voyez comment ça
I'm presenting, but after lunch, so I mean, whatever. I'll be around. We can stay together.
Once you do it for the whole day.
Yeah.
I'm more interesting by.
So okay. I didn't know that. Okay. So it's the important part.
And the difference with yesterday we had this long
Time. Okay.
which was very useful to kind of catch up.
So I will be okay.
Donc pour le chair après, là, il faut vraiment...
Even
11 minutes.
At 11 minutes.
Yeah, pour les questions. Non,
Better than 12.
ok, donc quand t'es chair, t'as pas de quoi te préoccuper. Ok. Ah ouais? C'est quoi? Et après on dit quoi le ok.
So for this, yeah. And sometimes you are getting like distracted and you cannot put in the current meter and you are like, no.
Ah, on the way to the food?
No.
Like
So in the 2 minutes, I was like, and Sarah was telling me like, I go, oops.
C'est moi, c'est pour ça que je te demande, parce que c'est moi, oui. Oui. Je vois bien que tu veux pas me répondre, mais...
Yeah, that's
Oui, Diron, j'étais bon, d'accord.
That's the point that you can say something like that, like more strict or whatever. More strict. Or I don't know if Olivier is gonna tell, but
Do we say it?
no. Okay.
It's just l'ami. At 7:38.
Yeah. The point is that at the end of the I will tell you. Yeah.
But you
No. At the I will tell you like 1, 2, or 3 questions.
Good morning, everyone. How are you this morning? Okay, that's a new day. Yeah, we lost a lot of people. Wow, it's only 9 a.m. So okay, so we don't have any specific announcement for this morning, apart from the fact that tonight is the dinner gala. The gala dinner. So it will start at 7-ish. Okay. And so it's downtown, and you have the address on the WhatsApp. It's been sent to you this morning. Otherwise, it's in the program. and you know where to find the program. Okay. Okay, that's all for me, and I'll give the mic to Sarah and enjoy.
So, thank you, Lizzie. So our plenary this morning is Marlène Gannon. So she's a researcher at the CNRS in Lyon, LBBE, and also at the Center for Biodiversity Dynamics in Trondheim. And she's a population ecologist with strong background in evolutionary biology and population dynamics. And she will tell us more about her research. Thank you, Marlène. So good morning, everyone. It's a very great pleasure for me to be here, and I would like to thank the organizers for such a nice meeting. So today I'm going to talk about biotic interactions and how they shape vital rates and population dynamics. Okay, so the size of natural populations fluctuates over time, and it's due to the combination of different environmental factors, such as abiotic factors, such as anthropogenic factors, but also due to the effect of biotic factors. And beyond population size, all these environmental factors influence individuals themselves, such as vital rates, like survival, reproduction, or their dispersal abilities. And in turn, it influences population size. So today I'm going to focus more specifically on the role played by biotic interactions and how they shape vital rates and in turn population size. So when we think about biotic interactions, we think about density dependence. And now we have a very nice overview of density dependence thanks to the great talk from Mathieu. So density dependence is classically studied through the phenomenological relationship linking the population growth rate, lambda on a log scale, to the population size. So then to estimate the strength of density regulation, you can just look at the slope of this relationship, beta. But by doing so, you make a strong assumption, that is that all individuals in the population have equal competitive abilities. So they all are equal in terms of competitive effect on each other. But of course, we know that individuals in a population may differ in their competitive abilities. For instance, in age-structured populations, we can think that individuals of different ages will have different competitive abilities. So how to account for that? The idea is, instead of having here the total population size n, we can split this total population size into age-specific population sizes. And if we consider a population with 4 age classes, for instance, then we can have here age-specific population sizes N1, N2, N3, N4. And by doing so, you can estimate the beta coefficients here that give you the age-specific contribution to density dependence. So how much the number of individuals, for instance, in age class 1, will contribute to the density regulation acting on the population growth rate. And by doing so, you can relax the assumption of equal competitive abilities and really account for the age-specific contribution to density dependence. So what we did is that we applied this approach on a well-known long-term monitoring of a great heat population in the Netherlands that is monitored since a long time by Marcel Visser. So in that population, there are several demographic data that are collected. In particular, we have information about the annual number of breeding females. We also have capture-recapture data for non-age females, and also recruitment for females of non-age. And so what we did is that we analyzed all these demographic data together using a Bayesian integrated population model to estimate the population growth rate, so the annual population growth rate lambda, and the annual age-specific population sizes. And we consider 4 age classes in that graded population. So first, we applied the classical approach to estimate the beta coefficient, and you can see here the posterior distribution of the beta coefficient. And you can see here that this beta value is negative, as expected, indicating that there is density regulation in that population. But then when we split the contribution of each age class, then you can see here, for instance, the contribution of age class 1 to the density regulation acting on the population growth rate. And you can see that this beta value is strongly negative, indicating that the number of birds in age class 1 really contribute to the density regulation acting on the population growth rate. Then here you can see the contribution of age class 2, which is a bit weaker than the contribution of age class 1, and then the contribution of age class 3 and 4. So the main conclusion here is that it's really the number of birds in the younger stage class that really contribute to the density regulation acting on the population growth rate. So we can really see that there is an age-specific contribution to density regulation. So if you are interested in knowing a bit more about the theoretical framework underlying this approach, you can have a look at this recent paper written by Russ Landy and colleagues that has been published this month in the American Naturalist. Okay, but still, when we apply this approach, we make another assumption, which is that interspecific interaction can be ignored. But we all know that species really don't live in isolation, but they live in interaction with other species. So it's important to account for different competitive abilities, but also to account for interspecific competition. So how to account for interspecific competition? So let's consider 2 species in interaction, so species A and species B. The population growth rate of species A may be written as a linear combination of the age-specific population sizes. So you can see here the number of individuals in age class 1 for species A and the number of individuals in age class 1 for species B. And you have exactly the same for age class 2. And by doing so, you can estimate the beta coefficients that are the age-specific contribution to density dependence, accounting for interspecific density dependence. And you can also estimate this p-value, which is a competition coefficient that varies from 0 to 1. So basically, when this coefficient is close to 1, it means that an individual of species A has exactly the same competitive ability than an individual of species B. But then, when this competition coefficient is close to 0, it means that basically interspecific competition doesn't really matter. And so then we are back to this equation, ignoring interspecific density regulation. So this is for species A, but we have exactly the same formula for the competing species B. We applied this approach on a well-known study system of 2 competing species. So the gray tit, our species A, and the blue tit, the species B. So these 2 species compete to get access to food resources, but also to get access to nest boxes. And what we did is that we took advantage of long-term monitoring of gray tit and blue tit at several locations in Europe. So 3 populations in Belgium and several populations in the UK and here to Oxford. And in these different populations, we have demographic data. So in particular, we have access to the annual number of breeding females. We also have access to capture-recapture data of non-age females and all the data to the Asian integrated population model. to estimate the annual population growth rate for the two species in all the different locations, and also to estimate the annual age-specific population sizes for both gray tit and blue tit in the different locations. And so then we estimated the competition coefficient P in the different locations. So here are the results. So you can see here the P value, so the competition coefficient for the gray tit, for the different locations, here the different dots. And you can see that this coefficient in most of the locations is close to 0, indicating that basically interspecific competition doesn't really matter for the gray tit. So the number of blue tits present in the population doesn't really influence gray tits population growth rate. And interestingly, when we look at the competition coefficient for the blue tits in the different locations, you can see that this competition coefficient is much higher, indicating that the growth rate for the blue tit populations is strongly influenced by the number of gray tit present in the population. So basically here there is evidence for asymmetric competition between the two species, with a strong influence of the number of gray tit on blue tits population growth rate, but basically no influence of the number of blue tits on gray tits population growth rate. Now, if we look at the age-specific contribution to density regulation, accounting for interspecific competition, here you can see the contribution of H class 1 to the density regulation acting on gray tit in yellow and blue tit in blue. And what you can see is that all these values are negative, indicating that the higher the number of birds in H class 1, the lower the population growth rate for both gray tit and blue tit. Now, if we look at the contribution of H class 2, you can see that in most of the locations, again, we have negative values, indicating that the higher the number of birds in H class 2, the lower the population growth rate for both gray tit and blue tit. But then, if we look at the contribution of H class 3 and 4, you can see that in most of the cases, the confidence interval really overlaps 0. So it means that the contribution of H class 3 and 4 to density regulation acting on the population growth rate is much weaker than the contribution of the youngest H class. So again, we found evidence for age-specific competitive effect, with the youngest birds having the strongest competitive effect. And if we compare the gray tit and the blue tit, we can see that they have more or less the same strength of density dependence. So in conclusion, we have seen that birds may have contrasting abilities to compete depending on their age, and that both intra and interspecific competition contribute to density regulation acting on the population growth rate. But now we can wonder what are the implications for the dynamics of age-structured populations. So we focus more specifically on one blue tit population in Belgium. So here you can see its population growth rate over time in gray. And what we did is that we tried to predict the fluctuations in population growth rate over time with the classical phenomenological approaches linking the population growth rate to the population size. And you can see that the predictions are quite far from the observations. So the fit of the model is quite poor in that case. So then we try to predict fluctuations in population growth rate over time, accounting for age-specific contribution to density regulation. And what you can see is that the R-squared is a bit better, indicating that we improve the model fit if we account for this age-specific contribution to density regulation. And finally, we accounted for both age structure and interspecific density dependence, and you can see that we really improved the model fit. So we get better predictions when we account for both age structure and interspecific competition. So you can say, okay, she has just selected the population that works very well in that case, but it was the case for all the populations we studied. So here you can see all the different populations. You have the R squared. The different numbers here correspond to the different locations, and equation 1 corresponds to the classical phenomenological approach. Equation 2 accounts for age structure, and equation 3 accounts for both age structure and interspecific density dependence. And what you can see is that as soon as you account for age structure, you really improve the model fit, and you again improve the model fit as soon as you account for interspecific density dependence. And it makes sense because we have seen that the number of great teeth has a strong influence on the blue teeth population growth rate. Now, if we look, again, better predictions when age structure and interspecific competition are accounted for. Now, if we look at the great teeth, so again, the different locations, we see that as soon as we account for age structure, we improve the model fit. But as expected, if we account for interspecific density dependence for the great teeth, we don't really improve the model fit because the number of blue teeth has virtually no influence on great teeth population growth rate. So it's important to account for age structure and interspecific competition to improve our predictions of fluctuations of population size over time. And it can be done using this function describing how different ages in two competing species may impact the population growth rate. So when we use this type of approach, we still make an assumption, which is that all individuals equally respond to competition. But we know that individuals may differently contribute to density regulation, but they may also differently respond to competition. And it's something we have studied in another study system. So we explored the interaction between two ungulates, so the chamois and the red deer, at two different locations in Switzerland. So these two species are competing for the access to food resources. So here you can see the two different locations. So at Waldrumschulen, you can see that the home range of the chamois in blue is strongly overlapping with the home range of the red deer in red. So in that specific location, we really expected a strong competition between the two species with the strong effect of the larger red deer on the vital rates of the chamois. However, at Euring, you can see that the two species are not overlapping. So here you can see the home range for the chamois and here the home range for the red deer. So we didn't expect any competition between these two species in that location. So to test for that, we used capture mark recapture data that have been collected on the chamois populations. So capture recapture data of non-age females and information about annual fecundity for each monitored females. And what we did is that we performed a multi-event capture recapture model to estimate annual age-specific survival rate and annual age-specific fecundity rates for the chamois. And as a measure of red deer density, we use count data. And so we tried to explore to what extent an increase in the number of red deer in the two different populations influence the vital rates of the chamois. So we didn't find any effect of the number of red deer on chamois survival at both Euring and Waldrumschulen. So that was expected because the chamois is a long-lived species. So we expected its adult survival to be buffered against environmental variation. So it makes sense. In terms of breeding probability, we didn't find any influence of the number of red deer on breeding probability of chamois at Ilfion, so in the site where the two species are not overlapping, so which makes sense. But we found an effect of the number of red deer on breeding probability in the site where the two species were overlapping, and this effect was age-specific. So if we look at the results, at Waldtrumschun, so in the site where the two species are overlapping, you can see here the breeding probability for the chamois and here the red deer density. And what you can see is that the larger the red deer population size, the lower the breeding probability for the chamois. And it's on females of age 2 and 3. So these females are primiparous females. We didn't find any effect of the influence of red deer on breeding probability for chamois prime age individuals. But for senescent females, so females older than 12 years old, we also found an effect. So the larger the red deer population size, the lower the breeding probability for the chamois. And here it's for chamois females that were failed breeders the previous year. So it means that for failed breeders, they tend to remain failed breeders independently of the number of red deer in the population. So to summarize, we found a negative effect of the number of red deer on breeding probability of chamois, but this effect was age-specific, influencing more specifically primiparous females and senescent females. So to conclude, we found evidence for age and size-specific response to interspecific competition with strong competition at Waldtrumschun in the site where the two species were overlapping. The chamois survival is buffered against changes in red deer abundance according to the demographic buffering hypothesis. But its breeding probability can be strongly impacted by the number of red deer, and this effect is really age-specific. And accounting for interspecific competition can be really important because it explains 27% of the observed variance in breeding probability for senescent females, and up to 90% for primiparous females, which is quite a lot. So to summarize this talk, biotic interactions really matter. Individuals may have contrasting abilities to compete depending on their age, and it's not a new concept. If we come back in 1973, Charles Worth wrote that in any particular case, the density regulation must occur in response to the number of individuals in a specific group of ages, which I should call the critical age group. And the critical age group might, for example, be composed of all individuals of reproductive age or newborn individuals, depending on the biology of the population. So to better understand density dependence, I think it's really important to identify the critical age group in the population. Individuals may also differently respond to density dependence. It's what we have seen with the chamois, but it's also the case with the gratids. So if we come back to the gratid study system, you can see here the recruitment on a log scale, and here you can see the number of birds in age class 1, and each column here corresponds to one age class. And you can see that the slopes really differ according to the age, indicating that there is an age-specific response to density regulation on the recruitment, but it's also the case if we look at survival. So here you have the survival and here the number of birds in age class 1, and again, there are different slopes for different ages, so age-specific response is quite common. And intra and interspecific competition really matter. It's what we have seen with the gratid-blotted study system. And in that particular system, for instance, we showed that including age-specific effects of intra- and inter-specific competition in density dependence may improve predictions of fluctuations in population size by up to 3 times, which is quite a lot. That being said, I would like to thank all my colleagues. I would like also to thank again the organizers for this nice meeting, and of course you for your attention. Thank you very much.
Thank you so much, Marlene. Do we have many questions?
Very interesting talk, thank you. I was just wondering, so of course for betas, let's say for the great teeth example, there is also difference in number of animals in the age classes. So have you looked at the betas normalized by the number of individuals?
Yeah, you mean if we standardize for the number of birds in each age class, because of course the population structure is biased in that population. So basically, in the great teeth population, we have a lot of young individuals. Of course, we have accounted for that. And we have also replicated this analysis on another study system with a very fast life histories like the great teeth. And we found that it's not always the youngest age class that will contribute to density regulation. That can be age 4, for instance, in some cases. So it's really depends on the biology of the species. Yeah.
Thank you for a wonderful talk. With respect to age class 1 having the strongest effect, do you think it's because individuals in age class 1 have the greatest influence on population dynamics, or because they're most affected by greater population size?
Yeah, it's a good question. I think it's both. So they strongly contribute to density regulation for the great teeth because they are new breeders. They tend to attend to new territories, and so they have strong competitive abilities for sure. But it's true that they are also the most influenced by density regulation. So I think it's really both. Yeah.
Thank you so much for this talk. It was very interesting. I have one question regarding what could be the explanation of why the great teeth didn't have any effect of the presence of the blue teeth and vice versa. What are the mechanisms?
The explanation for this asymmetric competition between the two species. So it's really based on the biology of the species. So the great teeth is larger than the blue teeth, and so they are a greater competitor over the smaller blue teeth. Yeah.
We have time for one more question.
That was a fantastic talk. Thank you. Very interesting. For the blue tit and the grey tit, you found no competition with effect with the 3 and 4 age class birds. I was wondering, is that a power issue because you've got fewer birds of fewer older birds?
Yeah, so it's related to this question. Of course, we have fewer birds in that category, but we standardize for that. So it's we accounted for the fact that the population is mostly composed of individuals of age 1 and 2 in the population. Yeah, we accounted for that.
Thank you so much, Marlene.
Thank you.
It's coffee break.
Thank you very much. Yeah, I want to make sure I understand what.
Yes, yeah.
No, don't worry now. I'm going to take it right now. Later. I always cover that all the time. It's even over the air, it's the Facebook chat. There's a grin and space. He chases people around. When was night and did you move to get there last night?
3.5, maybe 4, something like that.
I should call you or should you?
I don't. She has just standing there. It probably makes no sense to yes.
From this one?
On voit s'il y a des excuses. D'ailleurs, est-ce que
On voit la publication là-dessus. C'est ça. Et le présentateur, lui, il doit vraiment.
Even for me, I wanted to do it soon enough. See, this is what happens when I'm not I will ask you this.
Okay, so our next speaker. Ça marche ça? Ouais. J'attends. Non, j'y vais. Okay, so our next speaker is Matthew Silk, and he's going to be talking about demographic models of social networks. Thanks, Matt.
Right, hello everyone. I'm going to be talking about some work today that I've done here in Montpellier with Olivier Jimenez, just beginning to think about ways we might want to combine capture-recapture models of populations and social network analysis. And the reason I kind of think this is an important challenge or a kind of key part of linking behavior and population dynamics is that network structure, and today I'm going to focus particularly on social network, is a key way of linking population-level processes to individual patterns of behavior. And so we could think to start with about population dynamics. So for example, we might think of population size or population density shaping how individuals interact or associate with each other. A sensible starting point might be think as population density increases, you might expect more interactions or associations between individuals. But there might be more complex things going on. We might see sudden shifts in population dynamics, perturbing the social interactions or the social relationships of individuals and changing who interacts with whom in a population. Or if individuals choose to associate or interact with others of similar ages, we might see demographic structure also shaping the population social structure. But what I think is particularly fascinating about the role of social networks and social interactions in this is that we know from lots of research in behavioral ecology that individual social relationships are key factors influencing vital rates like survival and reproductive success. And this has been studied across a huge diversity of species from invertebrates right up to cetaceans. And this means that social networks and demographic processes are inherently linked together in this way. And this kind of feedback between the two is really important in influencing other ecological and evolutionary processes. So to pick one example, we might think about infectious disease dynamics. And this link between social behavior and demography is going to be really important in both explaining, for example, whether a pathogen can drive a host population extinct, but also whether a pathogen can persist in a host population for a long period of time. However, despite the kind of clear potential of linking together these approaches, it's not something that's been done a huge amount. And this is partly because when studying these things in wild systems, there are big challenges to address. I'm going to start with talking about some of the challenges associated with social network models and then bring in more capture-recapture models, and you'll see how the two don't necessarily mesh together very well. So when we're studying social networks, a big challenge is that the position of individuals within these networks is not independent of each other. If you think of a simple social measure, for example, such as the degree centrality or just the number of individuals you're connected to in a network, that's not just going to depend on your sociality, but it's also going to depend on the degree or the sociality of all of the individuals around you in the network. We might also face issues with covariance. So we might have situations where individuals that share lots of social connections are more likely to share similar values of traits. Or in some types of social networks, we might even end up in the opposite situation. So in dominance or aggressive networks, say, we might end up with patterns of negative covariance. And then finally, a major challenge is that relational data, such as social networks, are particularly sensitive to missing data. And this could be missing individuals or missing nodes in the network, so individuals that we haven't captured yet or aren't individually identifiable, but it could also be missing interaction or association data, so just missing observations of the social connections between them. On the flip side, we have demographic models where missing observations are incredibly common, and frequently we're dealing with situations where the status of an individual at any one point in time is a latent variable to estimate. Social network measures represent an example more often than not of time-varying covariates, and often in these situations, people use imputation approaches to deal with these missing variables and the fact that they change over time. So just as a demonstration, and I think we're going to hear more about this and a potential way to solve it in the next talk, Olivia and I just wanted to test what happens if we naively impute values of social centrality measures without touching the social network structure. To do this, we simulated social networks for a population of 200 individuals, and we simulated interaction patterns or grouping events based on these underlying social networks. We decided a relationship between centrality of individuals in these social networks and their survival probability, and we sampled from the data sets we generated to create what I'm going to call co-capture data sets. And this is simply capture-recapture data that also includes information on who was caught with whom. And then we just used standard approaches, simple approaches, to try and estimate this social and network effect on survival. And what we see is that while we typically, with well-sampled data at least, so with a probability of detecting groups being quite high, we see that the models are able to calculate the qualitatively correct direction of the effect. We consistently see this downward bias where we underestimate the social network effect of survival, at least in the social systems we were generating with these simulations. The extent of this downward bias varies a little bit according to which social network measure affects survival. So we started with strength, which is the S here, which is a local measure of centrality, which addresses only your closest neighbors or your direct connections in the network. But when we move up to global measures of centrality, which take into account the whole network structure, we see this problem is more exaggerated. Perhaps more promisingly, what we see is when we simulate no social network effect on survival, the estimates of the models are pretty good. So we don't have as many issues with there being kind of false positive errors or bias when there's no effect. Oh. We can then change various parameters in these models. So the one I'm going to focus on today is changing the probability of detecting groups. And so as we reduce the probability of detecting groups, we see this problem gets even worse. So the more data we're missing on interactions, the greater this downward bias gets, and we get to a point where we have qualitatively incorrect results, even potentially opposite results in the wrong situations. And so this highlights the challenge of kind of naively incorporating social data within capture-recapture models. But a potential solution to this is that instead of imputing the kind of variables we calculate for the network, is to more fully integrate social networks within capture-recapture models. In these kind of approaches, we can allow network structure or aspects of network structure, depending on data availability, to be estimated as a latent variable, and this can help mitigate some of the effects of missing social data. And so this is ideas that we're working on now, and we're trying to bring in expertise from social network analysis and social network modeling, as to be able to impute the network effectively requires good models of what's causing the underlying social structure. It's not something that I've got time to talk about now, but if anyone's interested, then I'm happy to talk with you afterwards. In order to kind of start this work and move things forward, we've developed an R package, GenNetDem, which can be used to simulate these integrated social network and demographic data sets. And so I'm just going to end the talk today by providing a quick overview of the R package. The first kind of functionality is that it's possible to simulate a wide range of potentially realistic animal social networks. So you can include individual covariates that cause variation in how connected particular individuals are. You can incorporate group or community structure to reflect group living animal societies, or potentially vary the extent to which position in space is important in structuring connection patterns. Kind of unsurprisingly, based on my introduction to the simulations, we can then simulate grouping events or interactions. So these could be dyadic, they could just be one individual associating with others, but they could be these higher order grouping events, which include more than two individuals at a time. We can then simulate social network effects on survival, so both incorporating a flexible range of social network measures and their relationships with survival probabilities, but also some of the covariance patterns that I talked about previously. And finally, there's a range of options or methods to create sampling designs, including varying capture windows and observation windows across a range of behavioral and demographic time steps. And so I think this provides this way of providing a combination of functions that can be, you can take little bits or others, so modularly designed, and creates a flexible workflow in which we can simulate different social network and demographic data sets, these co-capture data sets, which allows us to test model development and power analysis and study design, not only in kind of longitudinal social network studies, but potentially also as a tool for estimating the wider impacts of social structure and sociality on capture-recapture modeling. And with that, I'm just going to say thank you to Olivier in particular and the wider project team, not all of whom are on this slide, and people who I've talked about these ideas with over the last few years when developing this project. And I'm happy to take any questions that people have.
We just have time for one question, apparently. It's Javi besides. Okay, so maybe two questions, quick ones.
That was super interesting. Thank you so much. I was wondering, do you think, like, obviously you're at the stage of working with simulated data now. Do you think including these networks effects in the estimation of parameters will actually help making better predictions with population models later?
I think that will depend a bit on the study system that you're working with. So I can see situations where it won't necessarily overall impact the estimation of particular vital rates or population consequences, but I think there are also situations where it will. And I think especially for some social species where we might expect changes in social structure with habitat change or other anthropogenic pressures, for example, we might see situations where it's more important. But I think it's also important. We see a lot of studies in behavioral ecology that link traits like this or positions in social network to fitness without looking at the downstream consequences. And so I think even in situations where the downstream consequences there aren't really implications for population dynamics, that's actually quite an important result in its own right, to kind of separate the ecology and the evolutionary consequences a little bit more. So I think in some ways both are important, but I think you're right. In some situations, the overall effect on population dynamics will be more limited, and for some species, it's likely to be more important. And it's not really possible to answer that question without testing these things more.
And we have one question in the chat from Chris Sutherland. He's interested in using network metrics to explain colonization extinction dynamics in metapopulations, but when the occupancy states are latent. Do you think your approach applies in this case?
I think if you took these type of approaches that we're developing and you adapted them a little bit to be more relevant to movement or habitat networks, then they could be adapted fairly easily. But like, I think there's a couple of steps there to make sure that assumptions we're making about social networks or thoughts we're having about social networks not kind of implicitly carried out across to networks that are structured in a slightly different way. So yes, I think there's promise, but I think it takes a little bit of thinking along the way.
Thank you, Matt. Our next speaker is Javier. I don't know if I should pronounce it this way. He will talk about estimating individual survival under social network analysis when detection is imperfect. Thank you, Javier.
Hi. Hello, everybody. Okay, chapter 2. Social network analysis is a power toolbox for study strengths of association and interaction between individuals, social structure, information flow, and disease spread rates, and relationship between demographic and social processes. Mainly the data we used is the observed associations from all possible dyads from the n sample individuals. The association has, in all cases, 2 states, an associated or non-associated state. And this state is assigned by the researcher and is specific for the particular study. But when individual detection is imperfect, the observation of the dyadic state is imperfect too. So when association index are used for estimate the probability of association, it can be lead to very strong bias. So what is the probability association? So in the social network, the association probability is the probability 2 individuals are associated, and we can state the complement for the probability 2 individuals are not associated. So this state can change in time, and when detection is imperfect, we have to model that imperfect. And in 2011, it proposed a capture-recapture model for estimate the association probability according for imperfect and heterogeneous detection. Later, Jimenez proposed a closed multi-state capture-recapture model to estimate the probability transitions between association states, but both models assume demographic and geographic closure. So what the effect can be a demographic processes? Well, when an individual is permanently removed from a population, the connections are lost and another connection may appear. So in this context, it's logical to wonder if the individual survival is conditional of the level of association that individual may have in the network. So the objective of this work is to present and develop of a method for estimating the individual apparent survival conditional on the individual state when detection is imperfect. So I'm going to propose this model, and then I'm going to show you how I built this model under a SSM formulation. Then I'm going to show you some results from a simulation study to present the performance of the model. And finally, I present an example from a real data set. So to address this modeling, we need to define the association history. What is this? This is the history that follow the changes of the association state for a pair of individuals. So we have two levels: the individual level, which is represented by two capture histories, and the dyadic level is represented by the association history. So what tells this association history? For the first zero, we have no information for the dyad because we have a capture in the first occasion, but we don't have a capture for the second individual. And the second occasion, we can capture both individuals in association. For a state B, we capture both individuals in not association. So this is the name for two types of association. And we have a particular case when we capture just one individual and the other not. So we don't have information about the state. And finally, it's possible to capture no individuals. So this leads for uncertainty, and when survival is allowed, we can think that maybe association and not association is occur, but we can think too that one alive is dead and another alive is alive, and the other combination. And in the last occasion, there's a lot of combination, and appear a particular case when both individuals are dead. So when this happens, the dyad is deactivated permanently and no longer belongs to the social network. So this is an important thing to understand how the structure of the social change in time. So what can we do for model these changes and define, for example, two survivors? We use the Cormack-Shelley-Sieber apparent survival, and we can define a survival for individuals in association. For example, the first one is the probability that an individual survive and remains in the study area from T to T plus 1, given it was in association with the individual J at location T. But we have a problem because the individual, or for example, in this case, the individual 2 has a lot of states at the same time. So we cannot assign one survival to one individual. So my idea was to present some kind of weighted mean using the survival and the association probability. And this case is the same for the detection probability. So it's some kind of mix between associations. So this is the typical SSM formulation for Cormack-Joly-Sieber, and we can only estimate phi and p, survival and detection, but we don't have the information from the individual level to estimate pi, so or association probability. So we need to define a latent variable for the association state for a pair of individuals. So we have four variations. The first one is the dyad is associated and both individuals are alive and in the study area. The second is the dyad is not associated. Second, one individual is alive and the other is dead. And the fourth, both individuals are dead. The observation variable have four types, and the first is both individuals are not detected, only one individual is detected, both individuals are detected in association, so we have the information, and finally both individuals are detected not in association. So to construct this model, we use a multinomial trial. When we are in the first capture of the dyad, we need to track the state of these pairs, because it's possible to have two. 1 minute, okay. Because it's possible to have two individuals alive or one individual alive. So this can track by this one. So this is the detection matrix, and we're going faster. Theta, it's a matrix to track the dyad when the both individuals are alive or not. So I'm going to pass this very far to show you. Sorry, because it's to show you a case of study, because it's an application. We make a capture-recapture sampling, 5 sampling occasion. We identified 71 identified individuals, and we identified individuals with the notches of the dorsal fin. And we consider 2 individuals associated when they were fully identified at least once within a 44-minute interval. And for this case, we estimate these parameters. So these parameters of this model say very interesting things. For example, assuming no mortality, because we have daily intervals, we can say that 69% of the individuals remain in the study area after 4 years.
You will have to come.
Okay. Sorry. Okay. This is the thing. The apparent survival of associated and non-associated individuals show no difference given the data and the applied estimating method. Sorry, because the length of the talk. No, it's okay. No questions. In the break.
You can talk to Fabian. People can talk to you.
Okay.
Thank you. Okay, so our next speaker is Christophe Barbreau. and is gonna be talking about selection against immigrants, demographic evidence, and testing the familiarity hypothesis in seabirds. Thank you.
Good morning. So we had some great talks about immigration and how to estimate it and its biases. I would like to briefly talk about what happens after immigration. What are the immigrant fitness once they immigrated in a population? So we all know that the population dynamics are driven by four main rates: the birth rate, the immigration rate, the death rate, and the immigration rate. And the immigration rate, as it has been shown by some studies, can be very important for population dynamics, population persistence, and it has been shown in a few bird species in particularly. But it has also important evolutionary consequences, because it might act on gen flow, local adaptation, and this has been shown on fewer examples in experimental studies, and also in a few field studies. A pattern that is commonly found is that immigrants have lower fecundity or lower survival in some species, which is called immigrant invariability or infecundity. And this, as I said, it can impact population growth and extinction risk, but also gen flow. And it also can yield some selection for habitat preferences, ecological isolation, and then again on gen flow. And it can also lead for selection on divergence in mate preference, for example, and sexual isolation, which again can act on gen flow. And there are feedbacks between these processes which could lead to speciation. So it has potentially very important evolutionary consequences. However, immigrant performance compared to resident performance have been relatively rarely estimated in populations. So we like basically information on immigrant life history traits and fitness in the wild. And it has been mainly investigated in short life species like passerines or small mammals, except one long life species. And it's often based on single traits and it's not sex-specific estimates. So the objective of this study was to estimate the demographic parameters of immigrant individuals and resident individuals in seabirds, which are long life species, to compare these demographic parameters and fitness parameters, and then finally to test for trends in parameters, specifically to test one of the hypotheses that can explain the difference in performance between the two classes of individuals. So for this, we used data on seabirds that have been monitored for several years. One species, the wandering albatross, so it's breeding on Possession Island. It's a small island in the Southern Ocean. All the individuals on the islands have been ringed since the 1960s. So we know all the individuals born on the island, and the nearby islands here are potential locations for immigrants. The two other species breed in Antarctica here. It's the southern fulmar and the snow petrel. Again, we ring all the individuals in a small archipelago here, and there are localities for potential immigrants nearby. So a few words about the data. The capture-recapture study started in the 60s on the whole islands for these two species, in the 90s on the snow petrel. That's approximately the approximate number of nests that are ringed or checked every year. And we used the data from 95 for these two species and 2004 for this one, because we wanted to make sure that all the individuals born before the study were recruited in the population. So in this way, we were able to specify that all unmarked individuals that entered the population were immigrants. That was the way we could identify immigrants from residents, which were youngs ringed on the study site that came back. So we had imperfect detection for these three populations. That's why we use multi-state capture-recapture models. We use several states to properly model the life history cycle of the species, and you saw the life cycle 2 days ago with the presentation of Emmanuel and yesterday of Camille. So I'm not putting this horrible life cycle again here. And so that's the main strength of this study system, is that we were able to identify immigrants and to separate them from residents. And with that, we estimated probabilities of survival, return, breeding, hatching, and fledging. And we use in eSearch the counting algorithm to estimate the number of breeding events across the lifetime of individuals, but also the number of offspring fledged. And from these two, we estimated an average lifetime breeding success for individuals. So that's the results briefly. Here you have the 3 species, the demographic parameters here, the number of breeding events, the number of offspring raised, the breeding success, and the number of recruits also that we measured for some of the populations. And here a sex column that indicates whether there were sex differences or not. The brown cells indicate that residents have higher performance than immigrants. The white cells, there's no difference. And the blue cells, that's the reverse. So immigrants perform slightly better than residents. So you can see that in most cases, it seems that residents have higher performance than immigrants. And then just show you one example here on the wandering albatross. That is for the males. So you have the different parameters here, the immigrants in blue, the residents in yellow, and you can see that for some parameters there are slight differences with residents performing slightly better than immigrants. And here that's the same, but for the number of recruits produced by individuals during their lifetime, with more immigrants producing no recruits, whereas residents tend to produce more recruits across their lifetime. So that's nice to see that there are differences. Now, what we want to know, and the fascinating question for me is that why are there differences and how can we explain these differences? So there are several hypotheses to explain differences between immigrants and residents, but one that is testable for us here was the familiarity hypothesis. And this hypothesis states that immigrants arriving in a new environment lack familiarity about foraging grounds, social structure, etc., what we can imagine. And so this hypothesis makes several predictions. The first one is that immigrants have lower performance soon after they arrive in the new environment, that this performance should improve over age or relative age, so since first arrival in the new environment, that there are no intergenerational costs to immigration, and finally that immigrants' demographic parameters are more sensitive to environmental variation in the new environment. So I will not present everything, I will just talk about the first 2 predictions here. And so we fitted models where we modeled the demographic parameters of immigrants and residents as a function of age since arrival for these different species. So again, you find the species here, the demographic rates here, and immigrants or residents indicated by these 2 columns. The plus indicates that we found positive relationship between performance and time since arrival. And the minus, it's a negative relationship. And the green boxes indicates the results that are coherent with the predictions we made. So basically, that's where immigrants improve their demographic parameters, or some of the demographic parameters, as a function of time since arrival. The gray boxes here it means that there are no parameters because we didn't estimate the return rate for these 2 species. So what we can see is that in some cases, it looks like immigrants' performance tend to increase with age since arrival in their new environment, but it's not always the case. As you can see here for wandering albatrosses, we detected no effect for males, and we detected no effect for females, and even positive effects in survival and return probability as a function of age. So to conclude, we have found some differences in demographic and fitness parameters between immigrants and residents, and in general, immigrants in these 3 populations tend to have lower fitness than residents. So this provides some evidence for selection against immigrants in these 3 long-life seabirds. I didn't show everything here, but there are also sex-specific differences that are, and notably that females appear to experience less cost of immigration compared to males, which is quite coherent with the dispersal theory in birds in general. And some of the results support the familiarity hypothesis. So I would like to thank you for your attention, and would like to thank all the field workers that have collected all this data over the years, and Dominique Jopert for the data management, and the French Polar Institute and TAF for the logistical support for these studies. And if you have any questions.
So we have time for 2 questions.
Thank you for a very interesting talk. This is a question from someone who's never put a ring on a bird. Can they come off? Do you have to worry about tag loss in your estimation of immigration?
We put metal ring that are long lasting. When we see that there is some wear or damage on the ring, the birds are easy to handle, so we replace the ring so we can really follow the birds during their lifetime. So that's no a big problem.
Well, thank you, Christophe. Were you able to have a look at the role of pair bond experience? Because presumably the immigrants have to find a new mate, which most of time will be a resident.
So that's the project to do. We have a look at the pair bond effects and whether the sons and daughters of the pair bonds, how do they behave and how do they compare to sons and daughters of resident bonds. So that's the idea to continue on this project and to test for this type of a relationship here, because the proportion of immigrants in the population are not that big, of course. So if you estimate annually among the new recruits, the proportion of immigrants varies between 7 and 15–20% maximum. So that's not a huge number of birds. So most of the pairs are mixed pairs with immigrant residents. So you have no really immigrant pairs in this system.
So last one in the chat from Maron Nassiri. Thank you for this interesting talk. I may have missed that, but did you control for chronological age when testing the improvement in performance with time since arrival?
No, because one problem here is that we don't have the age of immigrants. That's a problem in this system because they are unringed, so we don't have the age. We have the age of the residents, but we didn't control it in this model. The ideal solution would be to find a way to find the age of immigrants. So we're looking for new techniques in methylation or something like that in the future.
Thank you, Christophe.
Thank you.
Our next speaker is Paul Cohn, that is going to be talking about close-kin capture-recapture models and seals in Alaska.
Okay, thank you. I'm going to switch gears a little bit. We've been talking here about traditional mark recapture a lot, which requires greater than one encounter of individuals. And the difference here is with close kin, we're using the fact that in sexually reproducing diploid species that each individual has exactly 2 parents. So that can kind of be interpreted as a mark and used to apply capture-recapture methods. So if normal capture-recapture is magic, maybe close kin is black magic. So we're going to try applying this to bearded seals, which are occur sort of around the Arctic. They're dependent on seasonal sea ice, which is declining, and they're currently listed as threatened under the ESA. They're hard to sample. Let's see if I can do this. Yeah, so we're sort of in charge of this sort of area right here, which is the Beringia, the distinct population segment. It's hard to sample. There's not many airports, so it's hard to do aerial surveys and very expensive. So our question is kind of whether we can use data from Alaska subsistence harvests to do close kin models and get a handle on abundance of this population. So the Alaska Department of Fish and Game has been sampling bearded seals in the subsistence harvest from about 2000 to present. They also collect premolars, which can be aged. And so we use those data and tissue samples to conduct some next generation sequencing and genotype those animals. And so we have over about a 20-year period, 1,500 seals that have been genotyped and using 2,600 loci to create a SNP panel. And then for the matches that we did find, we also conducted mitochondrial DNA analysis, which can tell you something about whether animals are related maternally or paternally. From those, the next step is to convert the genotypes to kin pairs, which is fairly easy for parent-offspring pairs. We actually found more than 2, but a lot of those were mothers and young that were harvested together. So we sort of took those out. And so we ended up with only 2 parent-offspring pairs and between 19 and 23 half-sibling or grandchild-grandparent pairs. You can't actually tell the 2 apart. You can't tell apart aunt niece either from that category based on genotypes alone, but full aunt niece requires there to be full siblings, which don't occur very often in naturally mating randomly mating populations. That said, for half sibling pairs, we do have sort of an overlap between them and lesser related pairs, such as half aunt niece and cousins and that sort of thing. So the way to deal with that is to sort of pick a threshold, discard any half sibling pairs in the lower tail, and then interpret the area under the curve there to the left of the threshold as a false negative rate, and to adjust probabilities with that. Let's see, so the inferential procedure we're going to use to analyze these close kin data is something that I kind of made up. It's called maximum joint pseudo-posterior inference, so we've got a couple of likelihoods here, one for parent-offspring pairs and one for half-sibling pairs. They're basically Bernoulli. We're comparing every individual to every other individual and asking, are they a parent-offspring pair or not? Same thing for half-sibling pairs, which can also be grandparent-grandchild. We're going to have some priors on some parameters and then also a constraint on finite population increase. And that's primarily because for close kin analysis, you want to have something like 50 to 100 kin pairs. And in this case, we have like 25. So a little under what we want. And I didn't really feel comfortable trying to estimate a population trend with that. Let's see. Okay, so then the fun part is trying to construct the probabilities of getting a kin pair match. And that's where we actually have things like abundance and survival entering into the likelihood. We're going to make some assumptions. So close kin models do make a lot of assumptions. One is accurate genotyping, accurate kin finding. I'm going to use an age-structured population model, sort of like a Leslie matrix model, just to construct some of these probabilities. Some assumptions related to heterogeneity and sampling as well, sort of like the mixing assumption that you would commonly get in capture-recapture models. And so the basic way to do this is to construct probabilities in terms of expected relative reproductive output. So for parent-offspring pairs, we've got some different probabilities based on whether the parent was a male or a female. So if I'm comparing 2 individuals, what I'd say is, oops, went the wrong way. So we'd have, for a potential male parent, it's the maturity of that male and the year of the young's birth. Remember, we have ages here divided by the total sort of reproductive output of males and the year of the younger animal's birth. Same thing for females, except we're using female fecundity, and then 0 otherwise. And there's some statements there where if the potential parent was dead at the time of an individual's, the potential juvenile's birth, then it's 0. So that's kind of how you construct those probabilities. I'm not going to get into the half-sibling pair formulation because it's kind of difficult. You need to integrate over the possible parents' date of birth and sex and so forth. And for for grandparent-grandchild pairs, that depends on sort of the pattern of mitochondrial DNA that's observed and whether the two share that or not. But one of the interesting things there is that's where you get survival information, because a potential, say, mother would have to survive from the time that the first offspring was born to the time that the second offspring was born. So that's sort of the real black magic of this. Okay, so there's a lot of parent parameters in what I just showed. And I'm going to basically say that fecundity at age and maturity at age are known constants, and that I'm going to put priors on this sort of blue survival curve, which sort of enter into the model, and then we're going to try to estimate abundance. So we get some results from template model builder here. We've got some assumptions having to do with the finite rate of population increase, some differences based on where you've set the half-sibling pair threshold for false negative rate. We did fit one model that had an extra parameter that permitted not all sexually mature males to reproduce. And that one came out saying about 40% of mature males were actually successfully reproducing. And each produced an estimate with a CV, which we found fairly reasonable, especially this one compared to aerial survey data. And we updated the CKMR model was able to update the survival from the prior. Okay, and so that's about it. So it's a sort of interesting way of trying to use samples from harvested individuals to estimate abundance and survival without any recaptures. But it does require you to kind of work with a team. I certainly don't know a lot about genetics, so it's good to work with a group of individuals there. And I guess I'm running out of time, so I'm going to leave it right there.
So we have time for 2 questions.
Thanks. That's really exciting to see this applied to a kind of low fecund species. You might have said that. What's the mating system in this species? So is it like polygynous males or monogamous?
Yeah, they're not monogamous. Yeah, it's sort of the males sort of hold these sort of underwater territories and sort of advertise to females through singing, and then the females have 1 pup per year.
Okay, and so do you have a sense if this could ever work for more monogamous species?
Yeah, I think that would be a little difficult. I've thought about that a little bit. I think the parent-offspring pairs are better there. When you start having the possibility of full siblings, it gets a little tough with using half-sibling pairs. So probably more useful in that case for abundance with. But not so much survival, because then you can't tell the aunt niece apart from the half siblings. Yeah.
Thanks, Paul. I'm curious about your thoughts on how opportunistic sampling may have influenced your results. Because they're coming from harvested animals.
Yeah, I mean, I think that you do get into the potential for problems there, especially if there's for more sessile animals that are maybe you know, close to specific places that you're harvesting, and so there's a question there of what population are you actually estimating? Is it close to where you're harvesting animals? And yeah, so that's a real issue. I think in this case, we're probably capturing most because you have sort of bearded seals sort of migrating up through these places where they're sampling, and probably most of the population is exposed to harvest at some point.
They're just one stock, right?
Yeah, just one stock there.
Okay, thank you very much, Paul. So our next speaker is Thomas Rieke, and he's going to be talking about latent fitness heterogeneity and structural equation models.
Okay, so what a pleasure to be here this morning. And today we're going to be talking about how we can use structural equation models to think about latent heterogeneity in fitness. And so it's incredibly important to understand fitness heterogeneity or heterogeneity in demographic performance, both at the individual level and at the population level. If we don't account for it at the individual level, then patterns at the population level and individual level don't match. If we don't account for it at the population level, then our projections of population change can be inaccurate. And so when we measure more than one demographic component, we often use multivariate normal distributions to model these types of processes. So we think about individual survival and reproduction as a function of population level means and individual random effects that are drawn from a multivariate normal distribution with variances for both survival and reproduction in this case, and a correlation between those two processes. So we might assume that individuals that survive at higher rates also reproduce at higher rates. But a recent paper from Remy Fay that I found really fascinating showed that there were tremendous problems with this approach. Specifically, we often overestimate the variances in different demographic components, and we strongly underestimate the correlations in demographic performance. And so I wanted to show you this visually, why this happens visually, and to do that, we'll have to do a quick analogy. This is in a very imaginative audience, so I think this will be quite easy, but I want you to imagine that the government of the United States has potentially made a mistake, okay? I know, this might be challenging for some of you, but just bear with me. And what they've done is they've printed a series of coins that are weighted. And this is actually impossible. There's a whole interesting side literature about this we won't get into, but some of these coins will be more likely to come up heads, potentially, and some of them will be more likely to come up tails. And any statistician might say, well, we can model this. We'll model each flip as a Bernoulli with a probability of heads that's specific to each coin. There will be a mean probability of heads at the population level for these coins, and each coin will have an individual heterogeneity, or epsilon. And so we would take a bunch of coins, and here each row is a coin, and we would flip them many times. And so we might get patterns like heads, tails, tails, heads, etc. And here the coins are all about the same number of heads and tails. And so we could quite easily say, if we did this with hundreds of coins and flipped them each dozens of times, that the mean probability of heads is about 50%, and that there is very little heterogeneity among the coins, right? So we would estimate sigma is bounded near 0. But wildlife data are very different. Anytime that we have a tails, this is analogous to mortality. And so the trial has to stop as soon as we have a tails. And so if you told this to our hypothetical coin statistician, they might be perturbed. This might be very concerning. And we also have imperfect observation of populations. And so here we might tell our hypothetical coin statistician that you can't look at many of the coin flips. And at this point, they would say, why are we doing this? This is ridiculous. right? And so here we imagine heterogeneity among these individuals, and we're trying to estimate that, but which one of these coins is more likely to have a heads, right? There's no information here. And so if we can't estimate what the heterogeneities are, what these epsilons are, then of course it's very difficult to estimate a correlation between these epsilons and some other demographic trait. And so because of this, unless we have data like Emmanuel Kem's Kittiwake data, it's going to be very, very challenging to have any precision for estimates of variances or correlations, because there's just not very much data. And so we know individual heterogeneity is very important to estimate. We also know that it's very challenging to estimate. And so the question kind of became, are there other simpler model structures that will allow us to ask the same question? And the answer is yes. And these are called structural equation models. They're similar and they're simpler. So again, here's our multivariate normal distribution, individual level survival and reproduction. We have individual heterogeneities that are drawn from a bivariate normal. And here's a directed acyclic graph for a structural equation parameterization. We have individual survivals and reproductions. We have a single heterogeneity that we call a fitness heterogeneity. We simply add this heterogeneity to one of our demographic parameters, and then we add it multiplied by a regression parameter to our other parameter. And we can do this for k number of parameters. So this is the number of parameters required for a multivariate normal distribution, where k is the number of demographic components that we're estimating. And this is the number of parameters required for a structural equation model approach. So we're asking the exact same ecological question with fewer parameters. And so we simulated a large number of data sets. Here, the rows are a number of years of study. The columns are number of releases, and these are multivariate normal in red and structural equation model in blue. The data were simulated with a multivariate normal model. So the first thing I want you to see is that when we have lots of data, we recover our simulated covariances very well with both approaches. They both work very well. When we have less data, our structural equation model estimates are less biased than our multivariate normal estimates, which are typically a little bit below zero. So they're a little bit below that one-to-one line. And this is hard to see with thousands of points. So here's a quick table. This column is the difference between truth and the estimate for multivariate normal approaches. And this column is the difference between truth and the estimate for structural equation model approaches. So we're farther away from truth, when using multivariate approaches, even though that's the data generating model. As Remy pointed out in his paper, we also severely underestimate correlations, right? So the previous slide was covariances. These are the correlations. These are consistently biased towards zero, even when we use the best available priors. And so structural equation models are more effective than multivariate normal approaches when sample sizes are small or limited. We also applied these approaches to real data. So these are some quite incredible data collected in Switzerland on breeding pied flycatchers and white-throated dippers. Just like when using multivariate normal approaches, we can reconstruct or derive relationships between demographic parameters like survival and the number of offspring recruited per year. So our highest quality dippers survive at much higher rates and produce more offspring per breeding season than our lowest quality individuals. Same thing with pied flycatchers. And we can also model effects of other covariates, such as senescence. So we saw declines in survival probability with age and increases in fecundity with experience, followed by declines with age, similar to what we would expect. And I'm going to skip this slide, or that's at 8 minutes. We'll talk very briefly. So what we're thinking about here is latent processes. And what I just described is a latent fitness, and we observe survival and reproduction, which are components of fitness. But we can extend these ideas to a huge variety of other applications. And so this is a wonderful example from Sarah's paper, where we look at multiple measurements of size, and instead of throwing away 3 of the 4, because they're all very correlated, of course, we include all of them to construct an overall size covariate. We can do the same thing with temporally varying covariates. So just out of curiosity, who here has had to remove a covariate from an analysis because it was too correlated with another covariate? It's like everybody, right? And so with our Dipper data, we have strong correlations between precipitation and temperature. Summers are cool and wet, or hot and dry. And this is also correlated with stream flow. And so we took these 3 covariates and constructed a latent dryness covariate. So instead of trying to choose between these 3 with model selection or making some ad hoc choices about which one to use, we put them all together into a dryness covariate and then use that as a covariate for our demographic parameter. So with that, thanks to my co-authors, there are 2 papers, one is in review and one is in preparation, Remy, Dan, Sarah, Madeline, and Mickey, as well as Johan Hegelbach and Pierre-Alain Ravison for creating these incredible long-term data sets on dippers and flycatchers. And these are some papers that I think are very interesting if you're interested in learning more about these approaches. And so with that, I'll take questions if we have time.
Time for one question.
Thanks for an interesting talk. So we've heard about magic and black magic, and I'm trying to figure out how black this one is. So like, is this something that can be relatively easily implemented in like the frameworks people use, like JAX, Nimble, and STAN models, or is this something that requires more specialist knowledge than the average statistical ecologist has?
Yeah, I mean, that's the model statement. And so you would add a prior for the variance. I think it's probably white magic. It's simpler than decomposing a variance covariance matrix. Or, yeah, it took me a long time to understand how these things worked. And then it was like, oh, okay, it's 2 linear models. Okay, great. Yeah.
Thanks a lot, Thomas. So next talk is going to be Blanca Sanso, that is going to talk about justice for the weaklings, survivorship bias in individual heterogeneity Semer models.
Hi everyone, I'm Blanca Sarzo, postdoctoral fellowship from University of Valencia, and I'm presenting this joint work with Ruth King, Rachel McRae, and Francie Corner about survivorship bias in individual heterogeneity capture models. So what is survivorship bias? Well, we all know that the stronger individuals survive longer than weaker individuals, but the problem is that the parameters are estimated based on those who have survived, and this is a very well-studied problem in areas of construction, forestry, and health, but not in the context of capture models. Within this context, this survivorship bias can be observed in the presence of individual heterogeneity. In this work, we are going to use the well-known core majority survey models, which are often applied to estimate survival and recapture probabilities, and they are conditional on initial capture. Parameters, as here, can be dependent on time, age, covariates, and also individual heterogeneity, but we will talk about this later. So when no individual heterogeneity is included, the likelihood can be expressed as a function of data, individual capture histories, and model parameters, survival and recapture probability. But what happens when individual heterogeneity is considered? Well, the likelihood has no longer a closed form, but it can be expressible as an interval in this way. And then we can use numerical or computational techniques to estimate the model parameters. Laplace approximation, Monte Carlo integration, Bayesian data augmentation. In this work, we have used in Gaussian quadrature as a computational technique, numerical technique. So when we realize about this survivorship bias problem, well, in a previous work, actually this is the reference of our work, which is a really nice piece of work. And we were working with a real database of around 3,000 guillemots ring at 6. And we modeled a survival probability as age dependent, temporal dependent, and also we include there the individual heterogeneity. So what happened? We expected that the younger individuals had lower survival probabilities than the older ones. As you can see here in this plot, age 2 individuals had lower survival probabilities than age 3+. I have to say that this database was a long-term database, so we have a really old individuals here. So that was the expected. But the problem is that when we look at the alpha age terms, we realize that the alpha term corresponding to 2 years old individual was quite higher than the 3 years old individual, and we didn't expect that. So what was happening? It was happening the survivorship bias problem. And why? Look at this plot. So the problem is that as age or time increases, the random effect distribution is moved to the right, because we are keeping only the stronger individuals. We are keeping the ones have survived. So we are not longer working with the initial H1 corresponding to chicks random effect distribution. We are working with a thin random effect distribution. We are moving to the right. So we realize that this problem we will going to have for when we were working with different initial ages at the beginning of the study. So although there is a common assumption that the individual has the same epsilon value along its life, we are going to consider that the random effect distribution is going to be different regarding the initial age that the individual entered into the study. So we are going to have a different random effect distribution for individuals age 1, 2, 3, 5+. So then the likelihood, the contribution to the likelihood for each individual has this form, where FA is the age random effect distribution depending on the age and initial capture. But what is the problem now? We realize about this, but what is the problem? Is that there is no, we will have an analytical expression for the thin random effect distribution for a given age. So we perform or we implement an algorithm trying to estimate the random effect distribution for initial age A. So we do it via simulation. First, for a large number of individuals, we simulate their associated random effects from a normal 0 sigma square distribution. And then we simulate their life histories. That is, see if the individual is alive or dead in the following category occasions. And then we use a kernel density estimation to obtain an estimation of the random effect distribution for each initial age, but considering only the alive individuals at this age. This is the key part. We have been working a lot of this, and we have performed a simulation study, but I have to say that this is a work in progress. We need to work a lot on this still. We have a lot of work to do. So in this simulation study, we again assume that the individual heterogeneity is on 5 on the survival probability. We simulate 6,000 capture histories, 6,000 individuals for 6,000 individuals. We consider only 2 different ages at the beginning of the study, individuals aged 1 and aged 2. And these are the real parameters. We use a frequentist approach and Gaussian quadrature for this simulation study. And what did we get? Well, on the left, here are the MLEs for the corrected for the correct model where we correct the survivorship bias, and this is the common model, a Cormack-Euring model. So as you can see here, alpha and p parameters are well estimated in both cases. However, for sigma parameter, our approach estimates perfectly and close to the real value the sigma parameter. However, the wrong model is not able to estimate it. So it seems that we are doing it well, but still, as I say, it's a work in progress, and we have a lot of work to do. For example, I wanted to comment that at the beginning we used a Bayesian approach, but it was computational and infeasible, so we need to change to the frequentist approach. Also, the algorithm needs to be improved in different ways. Also, we need to include more initial ages, because we consider that as many ages we have, more clear is going to be the difference between correcting or not correcting the survivorship bias. Go to a more realistic models where age and time dependencies on model parameters are included, and of course apply it to a real database, the one that I have shown you before. And that's all. As I said, it's a work in progress. We have a lot of work to do still, but we are happy with the first results that we finally have had. And that's all. Thank you very much. I will be waiting for any questions you have. Thank you.
Blanca is here, and we have time for 2 questions. Okay, Blanca, I'm going to ask you a question then. I take the opportunity. So have you tried, a very technical one, sorry. Have you tried the Nimble? And I know that they have specific algorithm that you can select, and could this be helping maybe? Oh, we don't hear you. Sorry. Okay. No. Oh, I think all is good on our side. No. Okay. Sorry. Oh, that's very bad. Yeah, so maybe I guess. Do you want to try to write the answer? But that's quite annoying. Or send us a vocal on WhatsApp. Yeah, okay, well, sorry, Blanca. We can thank her. And, again to all the great speakers of this morning, and now it's time for a break.
Un, deux, un, deux. Est-ce que vous m'entendez?
Je suis prêt. I was wondering, where is that? Yeah, I know. Neither. First is I want to know it.
It's on the first slide.
Okay.
You can say neither.
Yeah, but I know. It's just like I was checking.
Okay, no worries.
Because sometimes they put like I have to introduce them before I see slide.
Yeah, that's right. And all the co-authors are from Nina as well.
Okay.
Thanks.
C'est quoi ça?
Hello, everybody. Hello, so please be seated. Hello, so I'm Frédéric Barcan, and I will be chairing this session on the distribution and conservation of rare and endangered species. And so we'll start first with Brett Sandercock from NINA in Trondheim, who's going to talk about estimating venues and reproductive rates in the Arctic fox with multi-state occupancy models.
Thank you for the introduction. So today I will tell you a story about a conservation program for the Arctic fox in Norway. The natural history of this species, it's an alpine specialist. It's closely tied to snow cover. They have a very thick pelage. They switch coloration over the course of the year. There's several color morphs. And a lot of the demography is driven by a close tie to rodent cycles, lemmings, gray-sided voles, and it's the pulses of rodents that are very important for their productivity. And in Scandinavia, which includes Norway, Sweden, and a bit of Finland, they're in the naturally fragmented populations in the mountains, and then a lot of the connectivity among these sites occurs after the rodent crashes when the juveniles disperse. And the photo here at the lower left is one of 3 females from the Sjøfjellet area that picked up and moved about 100 kilometers, and then were running around in the suburbs of Trondheim, including this animal that was captured out at the airport. Which would be good for your yard list if you keep track of these kinds of things. On a national level, they're red listed as endangered in Norway, and the initial problem was overharvest up until the 1900s. At that time, an Arctic fox pelt was about annual salary for a trapper. So they were protected in 1930, and then they persisted at low numbers for a very long period and never really recovered. So the emerging threats are expanding populations of red fox, which are a competitor. And then some sites, so the lower right here is from a site in the southern part of the range at Finse, where there's been dampening and loss of the rodent cycles. So partly because of these ongoing problems, there was intensive management starting with a number of actions around 2005, which included the following programs. So we have a captive breeding program that's run through NINA. This is the site at Uppdal, about 2 hours drive south of Trondheim. So there's pens, there's pairs of foxes when they breed, and if there's successful breeding, then the pups are rounded up. So there's a snow scooter in the spring with boxes of foxes, if you will, that they're then distributed to a number of sites throughout Norway. And in some cases, these have been used to reestablish populations that were extirpated over the last century. In addition, there's been a network of sites with supplemental feeding. So these are, it took a number of iterations to come up with a design that was only accessible to Arctic foxes, and then it's mountain rangers taking dog food and stocking these feeders that the foxes have access to. And then it's a subset of sites, so the lower right here from Varangerhalvøya, also intensive efforts for culling of red fox, with hundreds of red foxes removed per year. So as part of this, there was 2 recovery targets set in the management plan several years ago, and that is the goal for recovery of this project was set to be 1,000 adult Arctic foxes at least 250 litters per year, with a target towards 2035. So for assessing whether we're getting close to these recovery targets, there's a lot of annual monitoring. There's annual reports that are produced each year. These are available on the NINAN website, and you can find them there if like myself, you enjoy reading in Norwegian. There's great information there. So one component of the national plan is this national monitoring of den sites. So the panel in the upper left is the timing of these visits over the year. Most of them are in the 6-month period between March to August. The first part of that is when the snow conditions are good, so the access is relatively easy. It's possible to go in with snow scooters or by ski, looking at the dens, looking for signs of tracks, scat, digging activity. The later surveys in July or August would be hiking in with a spotting scope, setting up on one side of the valley, watching the den site, watching for signs of both the adults or the associated young. And then all of that information goes into a national portal, Rovbase, which you've seen earlier in the conference. That was also used for the wolverine and wolf sampling. So a lot of the monitoring at den sites is historic den sites. So there's pretty good knowledge of where these dens were. So that's the blue line in the lower right-hand panel. But then only a subset of those dens have actually been used in the last 20 years. So that's the green line. And then a subset of those have been occupied by Arctic fox, and then fewer of those each year then are confirmed to have produced litters. So the uncertainty in going into a den and doing a den check is there's a lot of uncertainty in this process. So what we're most interested in is finding a pair that has produced young. And in this case, there's no uncertainty. We know the den was occupied by a breeding pair, and we know that it produced young. But more commonly, can go into the den and maybe an individual is sighted, or there's some indication of sign with activity at the den, but no young are sighted. And here, the den is occupied, but we don't know the reproductive status. And of course, we can also go to the den and there's no signs of activity. And maybe that's because there's been a recent snowfall, or because there's been rain that's washed away from the sign, or animals are away. Or in the case if they have pups, they can also be resting below ground, in which case they're difficult to see. And of course, the den could not be occupied. And then last, some of these sites are remote. So there may be months where we just don't have any information. So if I take all of the information from Rovbase over a 20-year period, it's about 9,000 visits to nearly 300 den sites, over 400 unique capture histories. And if you just scan and look through the capture histories, you can see there's a fair amount of uncertainty in the system, because there's lots of encounter histories, the green here where there's at least 2 different states, or the yellow ones where there's three different states within the encounter history. So the model we've used for analyzing this data is one developed by Jim Nichols and colleagues, and they developed it initially for monitoring spotted owls in Northern California. And it's a little different. If you're familiar with the multi-state models for individually marked individuals, it's a little bit different in that the occupancy states are in this hierarchy that I showed you in the previous slide. So we're assuming closure for the denning season, modeling the detection rates with monthly variation, and then the occupancy rates, looking at how that's changed over the 20-year time period. So the model parameters in this model include the typical state-specific estimates of detection for whether a den's occupied or whether it's occupied and young were produced. There's this classification probability. So what's the probability the observers get it right when they're doing a den check? And then the two occupancy parameters are, first, what's the basic probability that the den was occupied without respect to the reproductive state? And then secondly, conditional upon the den being occupancy, what's the probability that they produced young? And then it also generates a derived parameter. So what's the probability of successful breeding is the product of the two occupancy rates. Okay, so modeling the detection parameters, the color coding here, the blue is the probability of detection for an occupied den, the yellows for a den with young, and then the green here is the classification parameter. So there's a relatively low probability of confirming that the den is occupied, about 50% in the monthly visit, but it's quite a bit higher if there's young in the den. So close 80 and 80% and increasing over the season. So the classification rates here are 0 because this is before the pups emerge. So you have effectively no chance of classifying it correctly in these early months. And then that increases during the periods of the summer when the pups start to emerge up to about 70%. But then controlling for all of this imperfect detection, we can get estimates of the occupancy rates, which at first sight look very noisy, bouncing a lot within the parameter space. But there's two patterns that emerge. So the first is for the occupancy rates, there's evidence of recovery. So there's general increases in these two periods, and there's a reset here in 2008 that I need to talk to my collaborators about. But that's good news. There's a general increase in den occupancy. And then if we look at the breeding conditional upon occupancy, there's some interesting patterns here. So in the good rodent years, in the green box here, these are generally high, so 50 to 70%. And there's been an interesting change in what occurs during the rodent crashes. So in the early years, the conditional probability was really low in the rodent crashes, but it's increased in the last 2 years, and we suspect that this is an effect of the supplemental feeding, that it's buffering them. So we can take these parameter estimates and then look at how that relates to our recovery targets. So the number of dens occupied and multiply that by a breeding pair. That's probably conservative because we know there's floaters and subadults also in the population. But it's recovery, and if we say 300, 350 foxes, that's about 35% of the recovery target. And similarly, if we look at the recovery target for 250 breeding attempts, it's very low in these rodent crash years, but in the most recent years, if we calculate the number of dens by the product of the two occupancy rates, we're up around 100 breeding attempts, which is about 40% of the recovery target. So hopefully what I've shown you is this multi-state occupancy models are a nice flexible approach for modeling these kinds of territorial and den dynamics. The detection rates give us some information for designing the surveys. So we need at least 4 surveys for the dens occupied, but less than that if it's occupied by a pair with a litter. And overall, for the recovery of Arctic fox, it's encouraging. The den occupancy is increasing. It looks like the supplemental feeding is having some benefits. And we're currently about 1/3 of the recovery targets, but it's making progress, and the trends are in the right direction towards 2035. So with that, thanks to our funders, the Miljödirektorat in Norway and Naturvårdsverket in Sweden, and thank you all for your attention.
We have time for one quick question.
Very nice talk. With the supplemental feeding, is that distributed evenly across the landscape? And if not, is there any ability to test that hypothesis by stratification?
So the answer is no, it's not in all areas. Some of the supplemental feeders are put up in the vicinity of the den sites, so they're tied to dens. The challenge is that it went through several iterations at the start for the feeder design. So there's initial problems with, well, ravens and other animals being able to get into the traps and remove the food. And there isn't very good data on how effective the feeders have been. So it's sort of been more of a phased in approach. But it's a subset of sites, so we can certainly do comparisons for sites with and without feeders. But this was a recovery project, so the three management actions are kind of mixed in different areas. So it's a little bit difficult to tease apart the effects. Thanks very much.
So next is Sarah Baudouin, who's going to talk about wolves. So the title is Using Occupancy to Monitor Populations, the Wolf in France.
Hi, thank you. So the grey wolf in France came back in the early 90s from the Italian Alps. It is a protected species. As you can see here for the distribution in 2020, most of the population is located in the Alps. And the presence of this species is monitored via a network of observers who collect signs of the presence. So right now, the current monitoring of the population is based on population size, which is estimated with macro-capture models. And the data that is used are genetic samples from the collected signs of presence. However, as the wolf population increases in France, more and more genetic samples need to be collected so that we have enough recapture per individual. And also, as you can see, the confidence interval gets wider. So we've been exploring the alternative method to monitor the wolf population in France. So counting and survey, spatial explicit capture-recapture model, individual-based model, occupancy model. And the choice of an alternative method will be based on the field effort to collect the necessary data for this new method, the cost, the ability to detect changes, so to detect an area where the wolf just colonized and also area that the wolf just disappeared. This method also should account for imperfect detection and be part of an adaptive management framework. So we've been looking at a spatial indicator to monitor the wolf population in France. We reuse a dynamic occupancy model developed by Julie Louvrier, who should be in the room somewhere. So here are like two examples of occupancy map produced with this model with the color scale from 1 to 0, which is the occupancy probability estimated. And the idea is to calibrate parameter to turn these maps of continuous value into maps of occupied and non-occupied cell. So for that, we calibrated two parameters. So an occupancy probability threshold below which the cell is considered as unoccupied and above which the cell is considered as occupied. And also a buffer around the occupied cell to include surrounding cell. So to calibrate these two parameters, we try to match an alternative data set which represent pack occurrences and new colonization area. So it's the permanent presence area. We have the pack and the non-pack permanent presence area that are defined with the same data of the collected signs of presence. And so we try to match this data set with varying the two parameters. So we vary the occupancy probability threshold from 0.1 to 1, and we tried also 3 buffer size, and we tried to match 3 criteria. So the first one was to try to reproduce as much occupied cell inside this pack permanent presence area. So you can see for the combination of each value of the two parameters, we have like this color scale from 0, the blue, purple, to 1, the yellow. Yellow being like the parameter combination that maximize the number of occupied cells inside this packed permanent presence area. So we did that also for the non-packed permanent presence area, and also because we didn't want to overestimate the presence of the walls, we also had to maximize the non-occupied cell outside this permanent presence area. And then when we combine these three criteria, we can identify the best parameter combination to reproduce the wolf presence in France. So then, using these two values, we transform all our occupancy maps from every year that we have data for into the occupied and non-occupied cell, and then we compared it to our data set of permanent presence area. So on average, above all the year we had data for, we can see that 97% of the cells inside the packed permanent presence area were defined as occupied, and 71 were defined as occupied inside the non-packed permanent presence area. So we reproduce quite well the presence of the walls in France with this method. And also we have 97% of the cells outside of this area that are defined as non-occupied. So we don't overestimate the presence of the walls. We also wanted to see how this method could be sensitive to changes. So we checked when there is a new permanent presence area appearing. So we have 75% of the cells that are defined as occupied the first year that this area is identified. So it's pretty good at detecting the arrival of the wolf in a new area. However, we only have like 53% of the cells defined as non-occupied, where we have a permanent presence area disappearing. So it's a bit less efficient to detect area where the wolf just disappeared. So we also compared the change of the number of occupied cells with the change rate estimated with the population size. We kind of have similar trends. However, we can see that in the first year, the peaks are a bit out of sync between the two methods, and then the spatial, what we call the spatial indicator, so the change of number of occupied cells gets a bit smoother with the time compared to the population size estimates. So the idea is to use this spatial indicator to monitor the French wolf population, first at a large scale to evaluate the population trends with the change in the number of occupied cells, and also, and also at a local scale to evaluate the change of occupation at the cell scale. So here you can see the difference from one winter to the following, the cells that are still occupied, but also the ones that are newly colonized by the wolf, and also the area where the wolf got extinct or disappeared. So the perspective or application that we are thinking of is to combine this large-scale spatial indicator with local sampling to estimate demographic parameters like survival and recruitment. However, so far there is no change that is planned for the French monitoring of the wolf population to switch to this spatial indicator. So we need to do more analysis. Also, there is a work that is needed with the local stakeholder to explain this new method. And also there is a legal issue because the fact so far, because the wolf is a protected species, France has to report the management decision regarding the number of wolves that can be legally killed. And this is based on the population size estimate. So switching to a spatial indicator will have to change the way of seeing a thing for the number of wolves that can be legally killed. So that's it. Thank you for your attention.
Thank you, Sarah. For questions. So I had a question. I was wondering whether a lot of these occupancy probabilities seem very low all over France. isn't it an issue to set a threshold at like 0.5? Like, shouldn't we account for the fact that like the wolf can be present in many places, although the occupancy probability is fairly low? Like if it's 0.2, is it negligible?
Yeah, I wouldn't know like this how to answer, but the fact that we included detection probability into like the occupancy model, so we taken into account the fact that the species cannot be detected even if it's still present, and then the 0.54 that we have as the probability threshold is the one to both maximize the permanent presence area that we have identified, as well not over-representing wolves where we haven't detected the permanent presence area. And this method is supposed also to really represent the area where the wolf has settled down, where it's like permanently present and not just like a disperser coming through, and which could be represented by a lower occupancy probability, I guess.
Thanks. Sorry, there were questions but not related to this. One question.
Thanks for the presentation. I was wondering, in terms of the location of where it is allowed to kill wolves, is there any preference from the state or whatever, whether we should rather kill wolves where they are established, or if we should rather kill wolves where they tend to expand? Is there any special preference from the governmental decisions?
So for like the spatial distribution of the kill for the wolves, it's mostly determined by the attacks. So it's where you have like the most attacks on the livestock that you will have an authorization from the government to kill wolf in a certain area. But the idea of the culling of the wolf is not to regulate the population, it's to take care of like the conflict and the attack. So it's mostly for the spatial distribution, it's mostly based on the distribution of the attacks.
So thanks. So we move on to the next talk. So the next speaker is Anaïs Danon, who will talk about estimating breeding seabird population along the coastline at large scale.
Hello, everyone. I'm Anaïs Danon. I'm a PhD student and I work for Terres Australes Antarctiques Françaises and with the Centre d'études biologiques de Chizé. And my work is about estimating seabird population in the Terres Australes Françaises. Biodiversity knows declines, so that birds and especially seabirds. Seabirds are often breeding in remote areas such as the Terres Australes Françaises. And Kerguelen hosts 33 species of seabirds, but most of them remains poorly assessed. Why some of species are well known when others are not? Some of species are well visible, their population are accessible. They breed in large colonies and few large colonies, and some of them are emblematic. When others are hidden, their colonies are hardly accessible. They breed in sparse and small colonies, and they are unfairly misloved. So I am interested in coastline breeders. Species that breed in complex habitats formed by rocky coast or cliffs that make their prospections, very complicated in, for detection and localizations. This is a case of rockhopper penguins and Kerguelen shags. The other difficulty here is that both species breed all along the very long Kerguelen coastline and in small and very scattered colonies. This needs a very time-consuming, expensive, and complex logistic to prospect. Happily for me, the Réserve naturelle des Terres australes françaises, for the last 10 years, did these prospections all along the Kerguelen coastline, except for west of the archipelago. But those data are very heterogeneous in quality and in methods based. There are data that there are, observation took from the ground, others from the sea. There are observations that are only presence notifications, others that are counts of the colonies precisely. Sometimes they kept the tracks of the prospections, sometimes not. So I have a complicated data set. What to do with this? My goal with this was to estimate the whole populations of both species. So I did a hurdle model that is the combination between a binomial presence-absence model, for which I took all the data that were on the known prospected areas. And this is combined with negative binomial poisson or quasi-poisson abundance model, where you took account only of positive abundance. There is no zero in this. This is species distribution modeling. So I tested for the effect of different environmental variables that I want tell more precision here. Just a few results about them. CAT was a model selection based on Akaike information criterion, revealed a relationship negative and significant between cat's presence and the presence of both species and with the abundance of penguins. Moreover, another interesting result is that the elevation or slope that are the variables I chose to be a proxy of the coast relief was the variables that contributed the most to the explained part of the deviance of the presence and abundance models for shags and for the presence model for penguins. I also tested for the performances of the models in order to estimate the whole populations. And these are the results. So as you can see, presence-absence models were correct according to the area under the curves that were superior than 0.7. But the hurdle model, so the combination between presence, absence, and positive abundance was quite bad. This modeling was at the same time inaccurate and biased. So, at the question, can we estimate the entire populations? The answer is no, not like this. But by trying to reach this goal, we obtained other very interesting information about those populations. For example, if we interpolate the probability of presence of both species, we can highlight areas of high interest for conservation questions, such as at the middle, yes, the Gulf du Morbihan, that is a high present area of both species and is easily prospectable. And the north of Peninsula Courbet, here, that is already known to be an area of high cat predation risk on albatrosses that are very emblematic species. So why not on other misloved species? I would like to thank the Terre australienne Antarctique Française and the Centre d'études biologiques de Chizé and all the field workers for this beautiful data set. Thank you.
Thank you. Questions for Anaïs?
Yes.
Thank you for a nice talk. It's really great to see attention to these data deficient species. My question is, where did your cat data come from? How did you collect data on cats?
Yeah, I did not. It's the whole data of cats from the Réserve naturelle des Terres australes françaises that was gathered by my colleague in there. So it's estimation presence.
Okay.
It's just present absence of the cats.
Okay, cool. Are the cliffs around the whole island the same, like the same height and?
The same presence of cats? No, I think there are areas where cats are more present than others, obviously, but it's I don't know. I had those data, so I used them.
Yeah, good job. Thank you.
Thank you.
Is there another question?
Thanks for these great talks. In the nice maps that you show, we see that some parts of the island has much more use by the species than other parts. Have you an idea of the precise parameters that govern the distribution and that could explain that this part of the island has much more use than the others?
More or less. As I said, the coastal relief, so the presence of cliffs or rocky habitats, clearly is a driver of the occupancy. But maybe also there is an influence of the ability to the individuals to reach food areas, and I don't know more.
Thanks.
Thank you. So we're on to the last talk of the session, which will be online by Fabiola Iannarilli. And let me find, what is it? It will be leveraging sharing of camera trap data to inform biodiversity conservation at large scales.
Hello, thank you so much. My name is Fabiola Iannarilli. I am a postdoc at Yale University in USA. And today I'm going to talk on the work that we have been doing on how we can use camera trap data to inform biodiversity conservation on large scale. So why is this important? As it came out in the recent convention of parties that took place in December in Montreal, we need a collective effort to address the biodiversity crisis. And especially if we focus on life on land, on the goal of life on land, we cannot put the burden of managing and conserving and monitoring those species on the shoulder of countries that have already low resources. And so we really need to be strategic on how we optimize the data collection, but also how we use and reuse the data that has already been collected. In this framework, I think many important information can be obtained using camera trapping. Camera trapping allows to monitor simultaneously several species, especially terrestrial mammals so far, 24/7 with very low effort and very low disturbance to the species themselves. And with this in mind, many organizations that do a lot of camera trapping came together and built Wildlife Insight as a platform to help users manage the data, process the data, and soon also to analyze the data and get insight directly from those results, but also to share the data itself. Using information in Wildlife Insight, we are looking at whether and how camera trap data can fill gaps in coverage. And what we are seeing is that compared to what is already available in GBIF, camera trap data usually tend to increase the information that we have of species that are usually understudied and for countries that are usually underrepresented in biodiversity repo. Also, we can use the same data sets to understand for which species camera trapping is more promising. And for example, we can, body mass we know plays an important role on detectability via camera trapping. Here you can see the dashed line is the density distribution for body mass for all the species that are available at the location that were sampled in Wildlife Insight. And you can see that the species that have been detected in blue here are usually the ones that have higher body mass. But body mass is just like one layer here. If we start to look at other traits, we see that, for example, the time that the species spend across the canopy can play a role in how likely the species is to be detected. And so looking at all the different aspects, different traits, we can actually bring this information back on a map to understand where camera trapping can be more efficient and more useful to collect data on the species that we are interested based on their traits. So why is this important? Why we want more camera trap data? It's because this type of data is particularly information rich. And most of the time we are talking about detection and detection data collected over time. Data that we can use to quantify trends in occupancy. And as what we are trying to do here is to put together data from different projects, different sources to model those trends across the range. And I want to illustrate this using a specific example, the sun bear. In the left, you can see the range of the species in orange, and each dot is a location that has information about camera trap information in Wildlife Insight, color-coded based on detection rates at each location. This data have been collected during 11 different projects, and they add up to a total of more than 10,000 trap days, of which we had detection of the species in at least 130 of them. And if we overlap a 1 by 1 kilometer grid on top of this range, we have at least 700 cells for which we have effort and detection data. This is amazing, right? But there are like some challenges as well. Yes, the projects are fairly distributed across the range, but they don't cover the full range. And on top of that, there is like heterogeneity in how many years each project has been carried out. And so some projects have been collecting data fairly continually for like 5 to 10 years. Others have been maybe collecting data for 1 to 3 years. And if we zoom in, the effort is also quite heterogeneous. And here on the y-axis, you have the different cell. And in the x-axis, you have the full sampling period divided in 3 months period. And so you can see that of those within those 3 months, some have been collected, the data have been collected for almost continuously for the 3 months. And for other period, we just have like 1 to 3 weeks of sampling. So I've been thinking a lot about all the challenge of this data and how building a model to address those challenges, these and other challenges that I don't have time to talk about today. But sometimes the solution just came out while you are thinking about a problem. And one of the recent extension of the SP package developed by James Dozer and other collaborators has functioned to implement to fit spatially varying covariates dynamic occupancy modeling. And so as any occupancy modeling, the models are divided in 2 different components, one that describes the ecological process, one that describes the detection process. And the characteristic of this model is that along with the usual fixed term covariates, so covariates that are uniform across the landscape, we can also include covariates that vary, that are spatially explicit, so that vary across varying across the landscape. And this is in particularly important for what we are trying to do, because we are expecting the trends in occupancy to change, not just over time, but also across the full range. Seems pretty unlikely that an assumption of homogeneous trend across the range may hold for over like 20 years. In the occupancy part of the model, we also have first order autoregression process to connect 1 year to the next. The detection part, it's pretty straightforward. The only addition that we did is using project as a random effect to account for the different sampling protocol of the different projects. So using this data, we can actually estimate what is the trend in the mean occupancy probability across range here, for example, from 2003 to 2018, and we compare this information with expert opinion for biodiversity, for like informing biodiversity. However, we cannot, using this model, we cannot just look at the mean occupancy probability here. The mean occupancy probability suggests an increase in time of occupancy, but we can also look at the certainty that we have associated to that to those estimates, and we see that while the mean occupancy probability increase over time, we actually also the uncertainty in those estimates increase over time. So we need to take this positive trend with a grain of salt. And I think this is very important if we really want to start to quantify change in biodiversity over time and the effectiveness of the conservation action that we are implementing. This is just an example. This is preliminary data, so take all the plots that I've showed with a grain of salt. And before concluding, I really want to thank you, all the people that have collected, processed, and shared the data publicly in Wildlife Insight. The data are available to download. Each dataset has an associated citation that we are using when publishing this data, and we are pushing editors to really have all those citations, sometimes more than 300 citations, in the main text and not in the supplementary material of each article. And with that, that's something that we need to discuss as a community. With that, I would like to thank you all, and we'll be happy to take any question if there are some. Thank you so much.
So I think we have time for 2 questions, and there's already one on top. I hope Fabiola is hearing us.
Yes, I think I can hear you. Good morning.
Good morning to you too. Perhaps it's not morning.
Yeah, hi. Thanks for the talk. That was really, really cool. I had a question just about the map of where you showed where to, I think, place the camera traps, if I understand correctly. Was it just like the species traits and whatnot that you used to decide like the hot spots and cold spots, I guess, on the map of like where to place camera traps? Like, I guess I was kind of surprised to see like Canada's boreal forest, for example, have like relatively lower, just because I feel like that's like a fairly remote place that would be like good for camera traps. So yeah, I'm just curious, maybe to clarify what went into that map.
Yeah, so that model is built just based on traits. So it's body mass, activity during the day, the use of the canopy, and the diet. And I think the reason there is that pattern, so the reason why Canada and in general the temperate area are kind of on the low side is because it comes into that also the number of species that are available for detection, right? So in general, in tropical area, we have a higher number of species. So I think that's why we are seeing that pattern. It's so, and we are going, the next step in that is to try to understand where it would be good to a camera trap based on where we already have some information on the presence of the different species. Does that answer your question?
Yes. Yeah. Another question?
Interesting talk. I was wondering whether you all have thought about how to deal with the non-random sampling of where, or the non-random placement of camera traps. They're typically put in more pristine areas, and clearly that has some issues when you try and interpolate across the landscape.
Yeah, it's definitely like an issue, and it's hard to overcome, right? Because it's a bias of the data itself. We are using in the model like measure of like impact, human threats, and forest cover. So I hope that will help with that. But yeah, that's a caveat to have in mind. It would be nice to have more information from areas that are more degraded.
Great. So thank you again, Fabiola.
Thank you.
And let's thank again all the speakers from the last session.
So that's lunchtime. Thank you to go out on the left, on the sides, and go to Oui, Virginie, c'est Thibaut. On vient de terminer.
Ah, c'était dans la gauche.
Avec toi et tu fais pas. Oui, mais je le demande avec moi, je vais. Juste quand je. Parce qu'après, je dois. Le Zoom Link, tu vas sur mon avis.
Ouais, c'est ça.
Euring. Je sais pas si tu l'as, tu veux que je l'envoie. Je te l'envoie là. Hein. Là, je te l'envoie. Alors, moi, c'est. Voilà, mais ici, je. Tiens, t'as fait. Est-ce que tu.
Comme vous voulez. Hein.
Sur le chat, je vais le laisser là. Bah, du coup, faire le. Et après, je le file à Razir en vrai. Ah ouais. Plus que mon ordi, on le fasse 3000 fois. Ça te dérange pas que j'utilise ça? D'accord, ok. Bah ouais, ce sera plus simple de cette façon-là, ouais.
Ouais.
On va faire ça comme ça.
Ok. Je vais dans ce cas-là.
Ouais. C'est bon, c'est.
Okay, so everyone's here. So thanks, and maybe try not to sleep during this session. I know we are just after the lunch, but try to do a small effort. This is a session about a new approach for species distribution. And our first speaker is Marc Kelly from the Swiss Ornithological Institute, and talking about integrated distance sampling model for simple point count.
Thank you, Guillaume. Yeah, hello everybody. It's my pleasure to share with you my newfound passion for distance sampling. Here we go. Yeah. So integrated models in statistical science are really a mega trend. I mean, that's some of the biggest novelties, I think, in what we do here. So they could be subsumed under the topic of integrated modeling, where it's always about combining disparate data sets that inform about one or more shared parameters using typically a joint likelihood. And here's another example. So we had the following, that was motivated by the following problem. We had the problem that we had in a bird atlas project, both real distance sampling data, and then we also had point count data from eBird. And obviously they inform about kind of the same process or thing like density, and we wanted to combine them, but we didn't really know how to. Because for the point count data, there's a spatial mismatch between the two kinds of data, because for the point count data, we don't know the survey area they come from. And there is also a temporal mismatch because the point count data have a variable survey duration. In our analysis, we chose data from between 3 and 30 minutes duration. So how should we combine them? Okay, so this is kind of like these data can look like in the landscape. We have proper distance sampling data at some. We have other sites where we only knew that 6 individuals of the target species had been detected. And then we have yet other sites, perhaps where we only know that the species of interest had been detected at least once. And in other sites, it had never been detected. Yeah. So we have these 3 data types, which we call like the DS data, which are just the proper distance sampling data. We have what we call PC data, or the distance-free simple point counts. And then we have kind of the same variant, but just in a binary form, the detection, non-detection data. how do we combine them? After kind of a lot of back and forth, we came up with the following idea. We thought, actually, we can view the distance-free point counts, so the real point counts and the D&D data, as an aggregation of a latent distance sampling survey, yeah, where we do not have the information about the distance. And they observe the shame density process, and then the data type specific detection functions that we estimate, they address the spatial mismatch among the different protocols, and of course also detection probability. And we can also account for availability, different availability, but I'm not going to show this here in the talk. And the result of all that, we call integrated distance sampling models, and we have described it in a preprint there. And for about a year, we have been wrestling with ecology to get it through, so wish us luck. Yeah. So the basis of everything is really hierarchical distance sampling, where we work with bin distances because it's easier, distance counts here, at point transects, for which we assume a multinomial distribution indexed by a population size here, and where the cell probabilities are functions of a detection function with a parameter. We work with a half normal detection function, so the single parameter sigma that governs how fast or how slow detection probability declines with increasing distance between the observer and the bird. And then we have a model for abundance, yeah, which is typically a Poisson, but could be something else. And then we may have covariate models for the two parameters in the model, namely the density, and then the detection function sigma. And the whole, we have an observation model, we have an abundance model, and we have the covariate model, and the whole thing is really just a classical HDS model of Royle et al. And now comes a new thing. In a way, we want to describe the distance-free detection, non-detection, and point count data with a similar underlying process, yeah, the distance sampling. So for the simple point counts here, we adopt the binomial distribution for the observation model indexed by a population size as well, and by a site-specific detection probability. And now the new thing is that we express this detection probability as a function of an underlying hidden detection function here with a parameter sigma. Yeah. And then we combine together the sites by an abundance model, and we have covariates here. And so the whole thing is exactly the likelihood of a binomial mixture model, except that the new thing is that the detection probability is expressed as a function of this sigma parameter of a half normal detection function. And likewise, for the detection, non-detection data, the binary 0-1 data here, we adopt the Bernoulli distribution, of course. And where detection probability is again given by as a function of an integral of yet another detection function here with another sigma parameter out to some suitably wide truncation distance there. We have an abundance model here to collect the data together from multiple sites, and we have covariates. And so the whole thing is really exactly the Roy-Nichols model, except the detection probability here is expressed as a function of the detection function sigma here. So what we have now is we have in a way translated the different data types up to a common underlying currency. So we have likelihoods for each individual data type there, where we have a shared density model here for the three things. So the density model is shared, but we have data type specific observation models which are represented by the detection function sigma parameter. And we can build joint likelihoods assuming independence, which in this case here, I think we can confidently say means no shared sites. Yeah, so we can define these different integrated likelihoods here. And we think that we always need distance sampling data in the mix. We haven't tested this, but intuitively we're quite certain that this is the case. And we can get maximum likelihood estimates or Bayesian posterior inferences as well. We can also add in availability, and we have described this in the preprint, but I'm not going to talk about it here. So we thought we were really happy about the idea, but of course, we wanted to find out whether it really works. So we did simulations. We ran a lot of simulations, and here I only show two small ones really. First, whether we wanted to test whether we can really identify separate detection function sigmas in the mix of the distance sampling data with the other two types of data. And this is what the results here are shown here. So this summarizes the generation and analysis of 1,000 data sets, where we combined, I think, 250 distance sampling sites with 1,000 point count sites, or 250 distance sampling sites with 1,000 detection non-detection sites. Yeah. And the main thing is really this here, the central plot, where you show that what we estimate as a detection function sigma here for the distance-free point count data, the estimates lie exactly on the one-to-one line. Yeah, and likewise for the other data type where we combine distance sampling data with detection non-detection data also. So the regression of kind of the estimates on the true values coincide with the one-to-one line. Yeah. And the rest I think I'm going to skip. So it basically looks good. The other thing is in these integrated models, there's always also an interest about study design. So we can ask, I mean, what if we have these relatively cheap and less information-rich detection, non-detection data or point count data? Possibly we can go out and do a couple of distance sampling surveys and then in a way upgrade the cheaper data in such an integrated models. And as has been seen several times in such integrated models, sometimes it takes surprisingly small number of the more information-rich, more expensive data that we can add in a mix such that we can exploit the information from the cheaper data. So this is what we find here. What we see here. Here we simulated 200 sites with point count data, and then we added these numbers here of proper distance sampling data in the mix. And what you can see is that really, and the whole thing was like 1,000 data sets, so variability of the estimates of 1,000 data sets. So what we see here is really that with as few as 20 or 40 distance sampling sites, we can get estimates of in the integrated model, which are pretty good, which are kind of about the same as what we have when we add in about 100. Yeah, relatively small number. So we have a nice case study here in this beautiful American robin, got kind of the density map here in 2 counties in Oregon, and here we are. Yeah, so integrated distance sampling models, they combine distance sampling data with these distance-free, simple, what we call simple point counts, and the key to the whole idea is that we express everything as kind of the outcome of a distance sampling survey. Yeah, which may be latent in the case of the distance-free data. We can model availability if we have extra information as survey duration or possibly multiple observers. And there is lots of possible applications. I mean, mostly because there is such a superabundance of point count data around in breeding bird survey, eBird or bird atlases. There's also applications that are conceivable for things like acoustic ARU things. Yeah. And if you're interested, you can read this up here and hopefully somewhere else too. The development version of Unmarked has a new function IDS with which we can fit all 3 different types of integrated models here. So you can check that out. And yeah, it's easy to code this up in JAX or Nimble or possibly even Stan. Thank you for your attention.
Is there anyone with a question?
Great talk, Mark. Having the different surveys coming from different sites obviously makes combining the likelihoods easier because they're independent. But surely there's quite a lot of information to be gained if you have the different surveys at the same sites, because they're then estimating exactly the same detection function. That's basically.
I don't know from a design perspective whether it probably depends on what you want with your survey, but definitely, I mean, here we only worked with really separate size and independence, and I'd be interested to talk with Frédéric Barracon about what he thinks about this independence things, but that's what how we conceived it. In many real cases, you will have some overlap of sites, and then you have to separate. You have to write the likelihood in a different way because you have to account for this. I mean, there must be some dependence if you have repeated measurements in a way from the same sites. Yeah, so this is one way how we want to continue. Another thing is also, of course, usually here we only had a snapshot, so a closed model. But of course, I mean, we have these data over multiple years or so. So we wanted to somehow account for repeated measurements, for openness of the population. Yeah.
Thank you, Mark, for this great talk. In your point counts data, you had a latent truncation distance, if I understand correctly. Here.
Okay. I'm blinded by the light there. Yeah.
Yeah. So you had this latent truncation distance, and I was wondering, is that something that's estimated by the model, or is that something you have to provide?
No. So for the point counts, we made this truncation distance very large. I think it only has to, we have to ensure that every bird that appears in a count or that contributes to the detection, non-detection measurement will be inside of this truncation distance. So we made it very large, like about 1.5 times or 2 times as large as the largest distance in the distance sampling type of the data to ensure that no bird from outside of this radius could possibly be seen. I think this is we're convinced it's an innocuous assumption. It's just if you make the truncation distance too big, it will only have computational costs. Yeah, but it shouldn't affect the estimates. Yeah.
Okay. Thanks a lot. Thanks, Mark. This is Javier Fernandez Lopez, wanting a local one. I got a unified framework for estimating animal abundance from hunting statistics and a thin poisson point process model.
Thank you very much. Well, so I'm going to talk to you about this work that was developed with some colleagues from Spain, Sonia Llanas, J. Blanco, Joaquín Vicente, Pelayo Acevedo, and also with Olivier Jiménez from here, from Montpellier, from the CEF. So the first thing that I have to say is that as a Spaniard, I really know about the siesta after the lunchtime. So I'll try to keep your attention with some colorful maps, but if someone wants to take a nap, just go ahead. I completely understand. Anyway, so when we're talking about that, we were talking about abundance estimation during the whole week. So we know about all those methods, but those methods, when we're interested in abundance estimation at large spatial scales, maybe are not so suitable because they could be so expensive and the data that we have are scarce. So we can think about other kind of data availability as hunting statistics that have some advantages that I'm gonna tell you about that. They are available at broad scales. They contain more information than just only presence data, such as like in other citizen science data, like opportunistic citizen science. They are usually available from the administrations, and they have usually long-term temporal series. However, they have also some weaknesses, like they are usually provided at different resolutions. They usually came without effort measures, and also we have also a problem of the data reliability in the report. So here, our objective was to obtain as good as possible abundance estimates from only harvest data at high spatial resolution. Today, I will focus on the wild boar. And I'm sorry, because this is an ugly map. I'm not very good with colors. But I wanted to show you the different resolution, the different size that we have in the territorial units that we were using. This is the data that we have. We have like 1,000 hunting states, hunting grounds. And we have the data for the annual caught animals per hunting state for 7 different species of ungulates, wild boar, but also red deer, roe deer, etc. And we have also information about if the hunting ground was fenced or not. So The model that we were using is the thin Poisson point process. I have a slide with full of formulas, but I'm not gonna use it. I have this at the end of the slide in case someone is interested. So I'm gonna use this simple equation. So we were assuming that the harvest data, the number of total animals killed, is just like the multiplication of the number of animals in this hunting state times a thinning parameter. So this is what in the hierarchical terminology could be like the latent process, is the number of individuals we assume that are driven, is driven by the some predictor, environmental predictor in this case. And we assume that since we are obtaining the data for the hunting grounds, the total number of individuals in each hunting ground is just the aggregation, the sum of all those animals. And this is the tricky part of the model, that is what is called the thinning parameter. In the hierarchical methodology, it would be known as the observational process. And this parameter is the percentage, is a value between 0 and 1, and is the percentage of the population that goes into your data set. You can think about the different things that could affect this thinning parameter, like hunting effort, the catchability, but also some problems in the data report or sampling bias. So since we have no data about the effort for those parameters, we were using just the area about the hunting ground, if the hunting grounds was fenced or not. And here's the key of the model. We were using data about the rest of the species that were hunting in this territorial unit, because this is what is called also in the species distribution models area, could be similar to what is called the target group background, because we are assuming that by using the information of other species that were killed in this territorial unit, we have some information about the hunting managing on the hunting effort that is carrying in this specific territory. I want to tell you that there is also magic in this model, because this model, to avoid problems in the identifiability of the parameters, relies on the assumption that there does exist at least one covariate for each process that is not shared between those processes, which is called actually by many authors as the magic covariate, continuous covariate. So in summary, we started with wild boar kill per hunting state. We wanted to obtain wild boar abundance at high resolution. We used 70% of the data for calibration, 30% for testing. We ran the models by using Bayesian inference in Nimbo. And we did prediction assessment also by using field data. So more colorful maps, those ones are not that ugly. We were obtaining wild boar abundance at a high resolution level at 2 square kilometers resolution. And also we were obtaining spatially explicit predictions of this thinning parameter. The predicted total wild boar abundance was about like 370,000 individuals for the whole region. And we can see that we can also obtain like the predicted wild boar harvest, since we have just to multiply those two estimations that we have. And we can see that the predictions, the wild boar harvest predictions, were quite similar to the observed one. In terms of predictive assessment, we were obtaining quite good predictions when we were using the 30% of the data that was not used for model calibration. And then we used only 14 locations where field work monitoring is carried out by using random encounter models with camera traps. And we were obtaining kind of acceptable predictions, not very well, but at least they were in the same scale, you know, at the same range of abundance. So in conclusion, I just wanted to highlight this second conclusion, that is this idea that the data of other species harvest could be informing the model as an effort, as a way to measure this effort or this hunting management. And of course, for the future work, we are testing this for other game species, not only big game species, but also small game species and bigger spatial scales. And also, as you can understand from the previous talk about Mark, this paradigm of data integration is about to combine two different sources of data. One of them is usually widely available and highly available, but usually low quality. And all the other ones are like maybe more scarce, but more high quality. So the objective of this model was just to sit in the basis to then, in a second step, integrate more data from structured monitoring programs to obtain better abundance estimations at large scales. So I just want to thank you very much, and especially all the people that was involved in the field work. And thank you all for listening.
For 3 questions. So.
Hey, thanks for the talk. So I was wondering, you used the information from the other species to kind of help with your estimation. But I guess in some cases there might be a risk that how you harvest one species is a bit different, and so the effort required to catch a smaller animal would be different to catching a boar.
Yeah.
So I don't know, I just, do you think with the animals that you use that would have been a risk, or you think that they should be fairly comparable?
Yeah, definitively. Actually, we were trying different approaches. We were first using just big game species like red deer, roe deer, and these things. And then we were trying by combining both big game and small game. And actually, where the model was working bad with when combining those other species like rabbit, hares, or other species from small game. So definitively, you have to use like kind of similar species. The idea is just to use them because, for example, in Spain, we have some species that are mainly introduced for hunting, like the fallow deer or the Barbary sheep. So this contains like a lot of information about the sampling effort or the kind of hunting management that is carried out in this kind of territorial units. Yes.
Just over there. Interesting talk. When I think about these thin Poisson process models, right, the trick has always been, how do you identify the intercepts?
Yeah.
And so maybe what's the data that's helping you to get at the intercept there? And I missed that piece.
What's the data you say? Well, this is the slide that I wanted to show you. But yeah, we're talking about this intercept at the observational process, or?
Well, typically when I think of these models, like if you look at like some of the work that's been done by, I guess, D'Orazio, or like there was Royal's work, and either you have to make a parametric assumption about the shapes, or you have like an issue where there's the intercepts of the two parts of the model are somewhat confounded. So I was wondering how you got around that, or like priors, or.
We were just using priors and regular priors like normal, distributed, and white priors, non-informative, mainly non-informative. And yeah, we were making some simulations, because at first we had some problems with parameter identifications because we were using the predictor covariates for this observational process were categorical. But yeah, it has been known that you have to use this a continuous covariate that is not shared. So we had no problems in terms of the estimation, and actually we were like quite confident because we have like also field data, so we can compare the abundance. But definitely something that you have to take into account, especially, for example, we were not measuring, okay, maybe we have not the same continuous covariate in the different processes, but maybe those covariates are correlated. So yeah, for sure you have to take care about that. Yeah.
Thanks a lot. No more time for the question. So thanks a lot.
Our next speaker is John Grider, but from Colorado State University and Colorado Cohort Unit from the Field Generalized Research.
Thanks.
Yeah.
Thanks for being here. I'm going to talk to you about some work I did with the Colorado Cooperative Fish and Wildlife Research Unit, the U.S. Geological Survey, in particular, the North American Bat Monitoring Program, Bat Conservation International, and it was all funded through NSF. So we're looking today at a pathogen, the Pseudogymnoascus destructans, and it's the associated pathogen with white nose syndrome, which has decimated a handful of bat populations in the United States. It came into the U.S. in 2006, 2007, around where that red X is, and it's moved across the U.S. and Canada, and those warmer colors is where it's been found recently. It's characterized by this fungal growth on the skin of the animal, and this white nose is where the fungus that grows a lot on the nose, that's characteristic of where it gets its name. All of this data that we're going to be seeing today was done from people running out to hibernacula all over the United States and through Canada. They go around, they swab bats, they'll swab substrates in caves, they'll collect animals, and they go back and send them to a lab where they run qPCR on all of these swabs, and it comes back as positive or negative, and occasionally you get a suspect. But the problem with this is that there's some disagreement on the data, how it should be presented, how it should be analyzed in the lab. And even though you have this cave level, substrate level, or swab level, and qPCR run level, all you ever get is a single positive or negative from a hibernacula, no probability of detection, no estimates of error on anything. So the data that we're going to have today, this is it's 6 years of data from 2012 to 2017, and these are what all occurred during the winter. So the winter there would be 2011 to 2012. It's over 42 sites. This is the number of sites we surveyed in any given period, the sites that contained a PD detection, the mean number of swabs per site, and the naive site occupancy at those 42 sites over the course of the study. So again, we're trying to make more use out of this data. So we're trying to do a multi-scale dynamic occupancy hurdle model is what we've been using to analyze this kind of case study. So the multiple scales here are the hibernacula scale. In this case, I'll put a little cave up here. That at the hibernacula, you'll have multiple swabs. So you have the swab scale, and then within each swab, you'll have multiple qPCR runs. So over time, what you'll see is a cave will be negative. There's no white nose syndrome. There's no fungus. One swab goes positive. That's kind of what you get right now. They'll show you whether or not one swab has ever tested positive, but the problem is this prevalence changes over time throughout the course of the disease. So that's the dynamic occupancy. So that's the multiple scales and the dynamic occupancy. When you start to look at these qPCR runs, that's when we can get some continuous data that lets us implement the hurdle portion of this model. So this is our sample that we got from the field, and down here at the bottom is the cycle number. It's like a threshold, the number of times you had to amplify the DNA before the pathogen could ever be detected. And over here on the y-axis is the relative fluorescence. So there's this line at the bottom. When the fluorescence hits a certain amount, we can say we know that the pathogen is prevalent. We know that the pathogen is present at the site. So what we do is we take known concentrations of DNA, and we know how many times we have to amplify those known concentrations, and then we can build a relationship and start to estimate the actual load of the pathogen on every swab. So now we can get at site presence, site prevalence, and then the amount of load, the pathogen load within each one of these sites as well. So I'm going to be comparing that model, the multi-scale dynamic occupancy hurdle model today, to just like a standard dynamic occupancy model. This is what we're going to be comparing it to, which is you just have the Z state that varies by site by year. Your data coming in here at the bottom, which is just the swab level positives and negatives. And here's our model, which are some spatial covariates. It's an interaction of space and time, hibernaculum type. So this is just whether or not it was a natural hibernacula like a cave or a mine or a culvert. And then the probability of detection is left null. So here's the swabs coming into the data set. You get the swab level, which is going to be our prevalence in the data. We get 3 new equations for the swab level initial occupancy, the colonization there of the swabs, and the persistence of swabs at a site. So yeah. And then finally, once we get our 1s and our 0s from this data, we can begin to estimate our load, which is coming in at that qPCR level. And what we do is we take all the 1s and we multiply them by the mean and standard deviation of load across like in the middle case there, you would take all the swabs, the mean and standard deviation of all the swabs, and you multiply it by the Z stage of the cave, or you do a draw from it, and you get the effective load of a cave, and you can start to compare load across caves. And another interesting thing about this and using continuous data is that we can start to use the continuous data to monitor the probability of detection. So here we start to know a pathogen load at an individual run. We can say that the probability of detecting that pathogen in a swab is dependent on the amount of load on an individual animal when we're swabbing it. And it also is kind of fun because you can monitor probability of detection at 2 units. You can monitor the swab level probability of detection as well as the probability of detection in the qPCR run. In our case, this is null, and this is dependent on the critical threshold. So here's what that looks like, just pathogen prevalence by site and year. And I'll say this is our case study. I'm presenting the case study. We're still running a bunch of simulations on these. There appears to be a little bias, but the 95% credible interval does capture like the mean parameter. So within the case study, there's not a lot of difference here between the dynamic hurdle model and the dynamic occupancy model. With both of them just showing, the sites are all going to become occupied over the course of the study. And there's a little bit tighter credible intervals around the dynamic hurdle model. The one thing I will say that we have done with the hurdle model, the dynamic multi-scale dynamic occupancy hurdle model, is we have the ability to use like cave load. So cave load from the previous time step is now predicts your site level persistence through time. But here's the one interesting aspect that we can take away from this that you can't get from a standard dynamic occupancy model is that we have this prevalence through time, and we can also track the prevalence backwards and get a better understanding of the cave load and when the individual site was colonized and what it looks like through time. So these should be the right there is your standard dynamic occupancy model. The left is your multi-scale dynamic occupancy model. Everything that's not black is a positive. On the left here, you start to see we can actually get at the prevalence within these hibernacula, and it gives us a little bit better idea and understanding of what's happening as the disease progresses. I'm not going to talk about load today because I think it's going to take too much long. So we're just going to look at this prevalence over time. And where this really makes a big difference is in the early stages. So when you're just starting to detect these, just starting to get your early detections on the disease front. So you can see we start to pick up sites here in the far, far west at the same time steps. This is the first year of our data that we're never seen in the dynamic occupancy model. And that's because we're getting better detection and better estimates when we have very, very low quantities of pathogen within these populations. Not on the disease front, we see like clear pictures of what's happening in areas where the disease has been for a while. So I think these caves have probably been populated with white nose syndrome for 2 or 3 years now, but you can see in this region, which is like West Virginia, the Appalachian Mountains, there's a very different story of going on here with this cave has very, very low pathogen presence. So it just gives us a more clear idea of what's going on in the disease spread. Thank you all for your time, and I hope you learned something.
We have time for 2 questions. Just one over there.
Thank you for that. This seems like it could have a lot of application for eDNA modeling for invasive aquatic species, for example. Have you thought about those potential applications?
Yeah, so initially our model, I think maybe even in the abstract, I was talking about environmental DNA, and we were just swabbing substrate in these caves and using a lot of substrate swabs. So maybe there wasn't even a bat present in the hibernacula, but it was the probability of detection when you were swabbing an animal versus swabbing a swab were like very, very different. And it was the model just couldn't parse things out as well. But I think that's kind of where we are going with this. But since we only started swabbing animals, I kind of strayed away from eDNA because I think that community would like get mad because I technically had animals in hand. But that was the initial thought of this application was for eDNA in the environment. Yeah.
Is there any more questions?
You talked a bit about the management applications of the findings. So if we're seeing early detections in states like Missouri, is there anything you can do about knowing that there's virus there? Or is it just identifying the spread and how quickly the virus is moving across the US?
At this point, well, this data right here, this is from 2012. So if you could go back in time, maybe you could do something, but you'd have to bring a lot with you. At this point, early on, there was ideas of culling individuals that did not go over well. Now people have like developed vaccines. People have developed like ultraviolet light, just antifungal pathogens you can go in with and like start to treat populations. So on the disease front now, for instance, I'm in Colorado. The pathogen just showed up this year. It could highlight problem hibernacula. You could get there early and start to throw out treatments. Whether or not someone will get the funding to do that, who knows? But it's good, just building block now for the future. But you could start to ID some of those populations, see who's going to be most vulnerable early on, and try to get there ahead of time. Still in some areas.
Great, thanks.
Yeah, thanks. Thanks. Our next speaker is Florian Lagorseux. He's talking about niche model with unknown sampling efforts from unprecedented data.
Thank you. So hi everyone. A little disclaimer, short disclaimer before I start. I confess I'm a statistician, so I'm real. Please don't yell at me if I made some mistakes. And thank you to Javier to introduce all the sampling effort stuff. So today I will talk about how to inform niche model things using unknown sampling effort estimated from opportunistic data. So let's start with the data used here. We have passerines observations collected opportunistically by the rangers, not citizens, of the Euring National Park, which is a national park in the French Alps, between 1994 and 2022. And basically an observation is a result of three conditions: the presence of an individual of a given species, the presence of an expert observer, and the fact that the observer reports the species presence. So in contrast to protocol data, here the observer plays a role in the sampling process. So we have to take into account how the data are sampled to avoid bias. So we need information on the sampling effort, but it's not quantifiable. So we have to find approximations of it. So often a first class of approaches could be to use additional information thanks to other data sets like protocol data or GPA extracts. But what can we do if we don't have this data? The literature often uses proxies as roadmaps or human population density. But this additional information doesn't add temporal information and does not take advantage of the large opportunistic data set. So the second class of approaches is to directly find a proxy thanks to the large opportunistic data set. So in this short presentation, I will discuss one approach, which is to use observational counts of all the reported passerines on the regular grid as a proxy, with a first attempt to model this count process. The advantages to model this process are twofold. It allows smoothing the proxy and also to estimate the niche variability due to the opportunistic sampling. First, I quickly explain how I aggregated the data to have a spatial temporal count process. So the map on the left represents the passerines observations, the positions of these observations. We aggregated the data per periods to decrease the number of cells without any observations and to decrease the calculation time. So for instance, the observations between 1994 and 1996 are in the first period, etc. Then the observations are distributed by months. And finally, we applied a regular spatial grid of 1 square kilometer to have counts in cell. So note that when I when I say cell, I mean a spatial temporal pixel, that is to say a spatial pixel at a given month and at a given year. So the goal is given a cell, can we estimate how many observations do we have in that cell? And to do this, we use hierarchical Bayesian model, but as I said, I'm a statistician, so I use equations, so sorry. So, okay, let's see a cell which has the corresponding spatial pixel and the corresponding months and the corresponding periods. So we want to model the count, where is it? Okay, we want to model the count of all passerines in the cell C, which is denoted Y.C. We use Poisson distribution to do this, which depends on the volume of the cell and also on the mean number of observations, which is denoted lambda. We assume that this mean number is constant in each cell, and since it must be positive, we work with the log of lambda instead. We also assume that this number depends on it has seasonal variations, intervernal variations, and also spatial variations. So 3 kinds of variations, 3 terms here. The 2 first are independent and identically distributed effects. So the first represents the month effect, the second one, the period effects. And the last one is a month-dependent spatial field, which is here to spatially correct lambda given at a given month. Okay. So the model is fitted with the inner SPD approach, which is a certain way which is a fast way to estimate a certain kind of Bayesian model, which I will not develop here. Here are some outputs of the model. So we have the posterior mean of the predicted the month effect with a positive and a maximum effect in spring. We have the internal effect here, which is quite stable over the periods, which is consistent with the way we have aggregated the data. And here we have 2 over the 12 maps, you know, the WM term. So the first one is in January. The density is high in the valleys, which represents the fact that a lot of observations are in the valleys, while the one in July has a density which is more homogeneous and represents the fact that there is a rise in elevation of the observations in summer. So in the last minutes, we will model a focal species, again using a hierarchical Bayesian model. So it still depends on it is still a Poisson distribution, but this time we have also a term here which represents the proxy of the sampling effort. So this term is linked to the relative abundance of the focal species. We assume that it depends on land cover, land use covariates, but also on a spline cross effect between months and elevations to study rise in possible seasonal rise in elevation of the species due to the topography of the national park. Here we have a spatial effect, which could be understood as an unmeasured covariate, or which is here to explain correct for the spatially non-explained variation thanks to the covariates. And the last term is it's here to study interannual trends. Okay, so 3 models will be fitted. The first one without any proxy of the sampling effort. The second one using the raw count number of all passerines in each cell. And the last one using the posterior mean of the model presented previously. So to calibrate our model, we use the observation on the red crossbill, which is one of the most observed species in our dataset, with about 2,000 observations. The red crossbill, from what I understand, is a specialist species known to live in coniferous forest. So the idea was to compare the estimate of the parameter associated to the coniferous forest between the three models. So thanks to statistic criteria like DIC and AUC, we can see that the model without any proxy of the sampling effort performs much worse than the others. And more surprisingly, even for specialist species as the red crossbill, the estimated effect associated to the coniferous forest is not significant, while it is for the models using a proxy of the sampling effort. Note also that here the model with the simplest proxy seems to be better in this case. In fact, a possible explanation could be that the model has difficulty. It's difficult to model cells with high counts of observations. So, in perspective, I would like to try to model more precisely this high count cell and try and model other species, more general species, and also to use the same kind of proxies, but on the target group, target group of species, which no target group organ of species. That's it. Thank you.
We will have time for one question. Just over there.
Thank you for the presentation. I was wondering if you use the total number of counts as an offset, or because like if you use it somehow as an offset, is it really like the true abundance or density that you're predicting, or is it the relative abundance of that species compared to the other species? I was wondering which it is.
It's more the relative abundance, not the true abundance. In fact, we have discussions about using an offset or a covariate for this proxy a week ago. In fact, the use an offset is more linked to what we think about the sampling effort, but it's interesting to use a covariate because it's more the model has better predictions with better estimates, and also you can estimate a sort of is the species is sampled as the pool. I don't know if I'm really clear. I think it's possible to interpret something using a covariate thing to this the parameter.
Okay, thanks.
Thank you.
Thanks a lot. Speakers is Jamie Sunderland. It will be a remote presentation. And this is about innovation for biodiversity monitoring using acoustic methods in southwestern United States, and what does it mean for rare species?
Hello, and thank you for this opportunity to share some new monitoring research aimed at increasing the number of detections of rare species. To tackle this challenge, we have entered into a research management partnership with my co-authors Gavin and Brenda, also at Rocky Mountain Research Station, part of the research branch of the USDA Forest Service, Connor from Cornell Lab of Ornithology, and Valerie from the Kaibab National Forest, part of the National Forest Systems. Now, with a high diversity of birds in the southwestern U.S. region and multiple stressors on these populations, from climate change, drought, and wildfire, there is a need for monitoring approaches that provide cost-effective information on population status across broad scales. And as we all know, money does not grow on trees, so one of the biggest monitoring challenges his ability to efficiently allocate samples of species in space and time with limited budgets. Herein lies the problem. Multi-species monitoring programs are often designed well for capturing trends with common species. Multi-species monitoring objectives often include a mix of determining trends in community metrics and trends in focal species selected as indicators of something in the ecosystem. The something is usually trying to track changes with a rare vegetation type, which usually means those species that occupy that vegetation type are less common. In fact, most species in a community are rare, as well as being more difficult to detect. Thus, most species fall in this lower left side of the continuum. Therefore, as a quantitative ecologist, I recommend Research Station. My research team and I seek to solve this problem using a multi-factored approach with innovations in modeling and sampling to increase detections and inference on rare species and multi-species sampling frameworks. Today we are focusing on bioacoustics, but we'll touch on some other projects in the same region with data integration, citizen science, and optimal sampling. Wildlife monitoring technologies like passive acoustic surveys show great promise in overcoming these challenges to monitor multiple species at the same time. Innovation is more at the processing side, using automated data processing methods for multiple species. Passive acoustic surveys can be used to monitor unmarked wildlife communities, including multiple focal species and behaviors using one approach at reduced costs and over larger areas. In fact, there's been successes using passive acoustic monitoring in California and the Pacific Northwest of the United States, also showing promise in monitoring across broad landscapes. In the broader context of similar efforts occurring in other regions across national forest systems in the United States, we have three main objectives, with pilot studies occurring on the Gila and Kaibab National Forests, focusing on methodological and ecological questions. They are as follows: to inform management by co-producing science, identify challenges and opportunities unique to the Southwest U.S. related to passive monitoring, and finally, building infrastructure, efficiencies, and institutional knowledge for expanded acoustic monitoring in this part of the United States. Our case study is located on the Colorado Plateau with the Grand Canyon bisecting the forest. There are multiple vegetation types on this forest, including grasslands, pinyon juniper, ponderosa pine, mixed conifer, and aspen. The Kaibab National Forest has selected a few bird species as focal species on this forest. One of them is the Grace's warbler here on the left, selected for more open pine and pine oak forest, and then the ruby-crowned kinglet on the right for mixed coniferous forest. Now the ruby-crowned kinglet has much lower detection probabilities and is more rare on the landscape than the Grace's warbler, and thus we have less confidence about the data for evaluating trends collected so far. This is the same study area that we're exploring for data integration methods for species distribution models that are including point counts and eBird citizen science data for evaluating management effects on these focal bird species, and is specifically designed for increasing detections of the ruby-crowned kinglet to evaluate trends. And this is the wonderful research team on this project. And so far, we're seeing that the additional data source from eBird does increase the number of raster cells with ruby-crowned kinglets, the less common species here on the right, suggesting an additional benefit of combining data with this species. So we targeted one area known to be occupied by ruby-crowned kinglet and the Mexican spotted owl and other focal species within the Kaibab National Forest for our pilot study with acoustic recorder units in an area slated for treatment via mechanical thinning. We had co-located point count stations and acoustic recorder units to evaluate species detected by both methods to sample unmarked individuals at this time. For this area, we were mainly focused on sampling design questions. For example, we're interested at what density of ARUs we could see a leveling off of species richness. Thinking about optimal designs, is it different using acoustic recorders versus point counts, or what happens when you use both methods, as well as looking at the species detected with both methods, or one or the other, which ones are the same, which ones are different. Thinking about one of our focal species, what's the right ARU density to get at occupancy, and even looking at biological relationships with other species like the spotted owl and goshawk, since we have a high density of ARUs in the area. And thinking about what's the right density of ARUs and a unit of measurement across the whole landscape. We had 2 full months where ARUs were recording, and during the second month is when the point count surveys occurred. In true pilot study fashion, we learned a bit about other creatures that were interested in these recorders than birds. And also in pilot study fashion, we're still working on the pipeline for porting raw data into BirdNet and formatting for multi-species occupancy models. We do plan to have experienced birders assist with the training data specific to southwestern birds. We could, however, start to tease apart some questions on the point count data side. In our pilot study area with ARUs, unfortunately, ruby-crowned kinglets were detected infrequently, only one time, in fact, so we're hoping for better passive monitoring results. So to be continued. However, we were able to evaluate how increased point count effort in different parts of the forest and areas targeted for ruby-crowned kinglets, so mixed conifer, could increase detections. As expected, the number of species detected with more sampling grids had minimal impact, but the number of ruby-crowned kinglet detections in these areas increased greatly. Not only were we interested in raw detections, we wanted to see the respective increase in precision of different parameters of interest would be with respect to effort. So ruby-crowned kinglet occupancy, we saw an increase in precision with more effort for grid occupancy, but not for point occupancy. This is mainly consistent with our simulation study for rare species occupancy, whereby increasing the percent area sampled would increase accuracy. For species richness, at the grid or point, we did not see an increase in precision from just background point count surveys to mixed conifer areas and background surveys. So this is consistent with our simulation study, highlighting the difference in study designs based on parameters of interest. So with additional sampling method, passive acoustic monitoring and automated data processing, we expect to see more increases in detections. This has the possibility of strengthening forest citizen science partnerships and even adding an additional source to integrate with eBird and point count data for evaluating optimal designs. Finally, this increase in effort allows us to see increasing scales of answering avian biodiversity conservation and management questions. With that, I would like to thank multiple folks for the contributions to the projects. And with that, I would be happy to take any questions. Thank you.
Hi, Jamie. Do you hear us?
Yes, I can hear.
Good. Okay. We may have time for one question, just. Okay.
Cool. Yeah, hi, thanks. When you're thinking about the data integration side of things for adding the ARU data into the model, do you see that being something where it's like detection, non-detection data, or would you might start looking at like density, like trying to get density from ARU data as well?
Sure, that's a great question. And initially we're focusing on, presence absence, but definitely exploring the utility of getting at density as well. There's a lot of, advancements in that realm. So we're excited to get our hands on those data. Thank you.
Okay, so we don't have time for another question. So thanks a lot, Jamie. Thanks for all the speakers of this session, and I think time for a break.
Yeah, time for a break. A short break.
A short break.
Oh, no change of the slides that
No, but it's like for every GPU, so I don't need my it's perfect program. I'll have them on my phone as well.
And then they wish to I have to take the bus to the 1 hour population. Nice being there. Okay, thank you guys. I'm at least I mean, I've got some team, but it's great.
Probably not.
Yeah.
I will go on to Mummy Euring's morning post. The last talk. Actually, according to Shane. No, wait. And the last one's the 6th talk as well.
Yeah.
Okay. Go down on Twitter. So if possible, we would.
Yeah. Okay, yeah, no problem. All right, it's suspiciously quiet, so maybe we just get started. I don't see Olivier, that's why I'm hesitant, but maybe he already knows everything that's going to be said anyway. So this is the next stop on our long and winding road to the gala dinner. That's a session on communities and species interactions. And our first speaker today is Divya Jyoti Ganguly, who will be talking about data integration to study mesocarnivore co-occurrence.
Thank you. Good afternoon, one and all. Today I'm going to speak about some work that I did for my master's under the guidance of my supervisors Arjun, Divya and Uma. So we all know that carnivores play a crucial role in structuring ecosystems. But they can be really challenging to study. But why so? Because they are incredibly hard to observe, such as the Palaces cat over here. Which brings about data limitations when studying carnivores. And this is especially true in resource-restricted ecosystems, such as open natural ecosystems, where inherently lower densities of carnivores mean even lower detection probabilities. However, such ecosystems are also undergoing changes at unprecedented rates. And from a conservation point of view, it becomes necessary to understand how biodiversity, including carnivores, are responding to such changes. One way to go about it would be to actually try and integrate various types of data to understand species spatial ecology. And this brings me to my question, which was to assess how a community of mesocarnivores uses habitat and interact with each other in a semi-arid human use landscape in India. My study area was in the Kutch district of northwestern India, and the landscape here, as I already mentioned, is semi-arid, and it also hosts a diverse community of mesocarnivores inhabiting a mosaic of different habitat types. There are native open and wooded savanna habitats, and there are invasive Prosopis juliflora patches and croplands. These were the four focal species for my study. On the left, we have the habitat generalist golden jackal and jungle cat, and on the right, we have the habitat specialist Indian fox and desert cat. Apart from these, the landscape also hosts a lot of human and livestock activity, free-ranging dogs, and a growing renewable power industry, especially wind turbines, in addition to roads and settlements. Coming to my study design, I followed an occupancy approach to collect and analyze my data. I divided my study area into a grid network of 4 square kilometer cells, and I sampled these cells in 2 ways. So all the darker cells here were assigned for camera trapping, while all of the cells, including the darker and the lighter ones, were assigned for scat surveys. Going into the details, for camera trapping, I deployed 1 camera trap at the center of each of the dark cells, and here every 24 hours was considered to comprise one temporal replicate. And for the scat surveys, I divided the cell diagonals into segments such that one segment would comprise 1 spatial replicate. Now here it's important to note that these spatial replicates were assumed to not be along existing animal trails, because they sort of overlap many animal trails, which sort of is supposed to reduce issues with autocorrelation of collected scats. Now, as a result of these 2 approaches, I got a lot of species detection, non-detection data, which I integrated. And when I say integrated, I mean that I integrated them in the detection history, such that the first 14 occasions comprise detections from camera traps, while the last 8 occasions comprise detections from scats. To model species habitat associations, I used the single species, single season McKinsey model. And for modeling species interactions and co-occurrence patterns, I used the multi-species model as described by Rota et al. Here, co-occurrence is measured by the parameter F, which varies from negative values, which means spatial partitioning, 0, which means spatial independence, and positive, which means spatial aggregation. I modeled species habitat use and co-occurrence as function of both ecological and anthropogenic covariates. So under ecological, I used terrain ruggedness and the proportion of habitat cover. And under anthropogenic covariates, I used free-ranging dog encounters, and I scaled and summed up the distance to human settlements, the density of metalled roads, and the number of wind turbines per sampling unit into the human impact index, which I used as a covariate. Now, obviously, I was using 2 different detection methods, so I had to account for the differences in detection. For that, I used a survey-specific detection covariate, which was detection type. So I had camera trapping and its interaction with the camera trapping effort, because not all camera traps were active for 24 hours, and SCAT surveys. Next to the modeling workflow, to simplify things, I carried out modeling in 3 steps. The first step comprised assessing species habitat associations. In the second step, I assessed species co-occurrence patterns and checked whether free-ranging dogs had an impact on species presence or interactions or both. And in the third step, I assessed whether the human impact index, which is a measure of human impacts, had an impact on species presence, interactions, or both. Now here, the best supported model at each step acted as a foundation for the next modeling step. Coming to my results, through the fieldwork of 3 months, I was able to cover about 80% of the study area. And this involved 950 camera trap days and 127 scats collected over 400 kilometers of sign surveys, and yielded detections of 450 plus detections of 12 species of carnivores in the landscape. However, enough detections were obtained only for the 4 focal species, which were golden jackal, jungle cat, Indian fox, and desert cat, and hence the analysis pertains to these species only. Coming to the specific results of my objectives, the first one was to assess species habitat associations. And I found that open savanna habitats were the most important for most of the mesocarnivores in my study, amongst my focal species. So here we can see, and these are the beta coefficients, and in the brackets we have standard errors. And golden jackal and Indian fox clearly used open savanna habitats a lot more, whereas golden jackal and jungle cat tended to avoid wooded savanna habitats. Now, mapping these habitat associations showed that for most of the species, habitat use was rather patchy in the landscape. And this is interesting because most of these species are otherwise considered to be much more widespread and adaptable. The next objective was to assess the impact of free-ranging dogs on species presence and or interactions. And I did not find an effect of free-ranging dogs spatially. That is to say that there was no evidence to suggest that free-ranging dogs had any effect on mesocarnivore presence in my study landscape, and free-ranging dogs largely did not impact mesocarnivore co-occurrence patterns as well, except in the case of Indian fox and desert cat, which were less likely to co-occur in areas of higher free-ranging dog encounters. And the final objective was to assess the influence of the human impact index on species presence and co-occurrence. And for this, I found a consistent negative effect of the human impact index. That is to say that at least 2 of the canids, the golden jackal and jungle cat, Indian fox, clearly avoided areas with higher human impacts, which means areas with more roads and wind turbines closer to settlements. And 5 out of the 6 species pairs also tended to co-occur less in areas of higher human impacts. There are certain limitations to my study, and there is scope for improvement. For example, it is a dry season snapshot of species presence and interactions in a rapidly changing landscape. And to understand the processes underlying these patterns, we definitely do need data collected over multiple years. Next, I couldn't distinguish between desert and domestic cats using mitochondrial genetic markers, and as a result, I could not use any of the SCAT data pertaining to desert cats in my modeling exercise. However, that would have really helped, and probably would have also helped increase precision in some of the desert cat estimates. Next, I decided to combine the individual human impacts into an index for the sake of parsimony. However, from a conservation point of view, it would actually make more sense to look at these impacts separately, and this is something we are working on. And finally, other anthropogenic impacts such as noise, for example, from wind turbines, could also be affecting species presence and interactions. And although I collected data on the same, there were issues with processing the data, and I couldn't really use it in the analysis, or have not been able to incorporate it yet. Overall, our results suggest that an increasing human footprint in the landscape could engender increased competition in the mesocarnivore community, and could lead to competitive exclusion, potentially lead to competitive exclusion of competitively inferior species from the study area in the future, making sort of the carnivore community more homogenized and less diverse. And this study, this study also exemplifies a potential way of using multiple sources of data in large-scale studies on carnivores. I would appreciate questions, comments, feedback. Thank you.
Thank you very much. We have time for one quick question. Yes, please.
Thank you for an interesting talk. I was just wondering about the effects of dog presence and how the distribution of dogs look like across the study area, because sometimes the effect could be, the lack of the effect could be simply because of lack of heterogeneity, and the dogs are everywhere. So have you looked at that? Thanks.
Yeah, thank you for that question. And yeah, correct. So I think what you said is correct, that there is a lack of heterogeneity in dog presence, or maybe it's not heterogeneous enough, because dogs seem to be using much of the landscape a lot, and potentially the effects of dogs are apparent at much finer scales only. So yeah, that's something.
Great. Thank you again very much for your talk.
Thank you.
And our next speaker is my colleague, Julie Louvrier from the Leibniz Institute of Zoo and Wildlife Research, and she will be talking about how much data we need to study co-occurrence using multi-species occupancy models.
Thank you very much. Thank you very much for inviting me to come here. It's always very nice to come to Euring, so I'm very happy to present the simulation study that we conducted with Mason Filino and Olivier. It is work in progress, so any comments or questions are very welcome. And so basically we wanted to study a little bit this multi-species occupancy model and try to see which monitoring schemes, in which type of monitoring schemes this model would perform best or better. And we found some quite interesting results. So now that I have your intention, until the end of the talk, we can get started. So I'm going to kick some open doors, as Kilian said a few days ago, but to get back into the principles of occupancy, it is a proportion of an area occupied by species. It can also be defined as the probability that a species occupies a site at a given time. It can be a function of biotic and abiotic factors, or covariate. To establish an occupancy model, traditionally, one needs to have a study area and select sites on which they go regularly. They have regular visits and have observation points, detection, non-detection. And occupancy models are kind of also magical, because one can actually estimate whether a site is occupied, even though no detection, it was only non-detection, as you can see here on this top right site. So now the model that we wanted to investigate in this context was the model developed by Rota and collaborators in 2016. The one that, and we used actually the package unmarked. So we're going to talk about two species, and I'm going to use animal silhouettes because I like animals, and it's always nice to keep in mind what we're talking about. So we're going to talk about a predator and a prey, but we can talk about dominant versus dominated species, but here in this case it will be predator-prey. We have a species A that is present at a certain site. We want to investigate whether or not it has an influence on species B, which is going to be the prey in this case. And we want to know basically what happens when we have those four situations. When both species are present, so this is going to be quite a tricky thing to say for me, so bear with me. So we have psi capital B, capital A, which is the probability of the prey species to be present given the presence of the predator. Psi capital A, capital B, which is the other way around. And then at a site where only the predator is present, it's psi capital A, small b. It's almost done. And then we have for the prey, we have psi capital B, small a. So the presence, the probability that the species is present given the fact that the predator is absent. Okay. Okay, so now, just to get back a little bit into the concepts, when we're talking about interaction, we're actually looking at the proxy for interaction. We don't measure species interacting per se, but in our case, I will talk about interaction for an easier speech. But here in this case, when we talk about interaction, it is the conditional probability of occupancy given the presence or absence of another species, but in that case, interaction, because it's easier. So we built 7 interaction scenarios along a gradient from no interaction until high interaction. So the first scenario, there's no interaction. We have the probability of occupancy of the predator, which is 0.7. And here we can see that the species, its probability of presence is the same whether the predator is present or absent. Then we have a low interaction scenario. So here we have 0.5 and 0.6. Here you will see that the predator, the psi of the predator is always the same. The only thing varying is the psi of the prey. So here we have the low medium, then we go further, we have 0.3 and 0.6. And then I checked this, and I'm sorry about that because I was convinced that I changed the numbers, but it turns out there are some mistakes on the slides, and I'm sorry about that. So it's actually 0.2 and 0.6, further 0.1 and 0.6, and then a really high interaction scenario, 0.1 and 0.8. So really avoiding the predator. So then we wanted to test how many repetitions at a site one needs to have in order to have the best type of performance from this model. So 3, 5, and 10 repetitions. We wanted to test for the number of sites, so 30, 50, and 100 sites. And then we actually worked with the probability that the species might be at least once detected at a site. For the species A, the predator 0.6, and species B 0.8. So quite an ideal scenario in the occupancy world. I don't know about you guys, but it's actually, those are really good occupancy detection probability. So yeah, it's the probability that the species is at least detected once during the repeated surveys. And we repeated this for each scenario 100 times. So what happened? Okay, this is quite a lot. But basically, we're looking at the estimation of the parameters by the model. What we can see here, the red lines are the simulated values, and the box plots are the estimated values. We are here in the setting when we had 30 sites. On the top is 3 repetition, then 5 repetition in the middle, and 10 repetition. Doesn't look too bad. But we can see that the precision is not too bad, but then we have, some estimations are a bit more broader, have a broader uncertainty than some. So basically, okay, I will go fast on the next 2 ones because then it's 50 and then it's 100. So we can see that if I go back, it gets bigger, and then the more we increase the number of sites, the more precise. Makes sense? That's good. So another way to show the results is by measuring the mean squared error, so the precision. We can see here that when we have psi A, actually we have the 3 in purple are the 30 sites. So this is when we have the worst type of precision. And then the 100 sites are the lines that are more in the yellow type. And we can see that with the number of sites, we have the precision doing better for the 3 parameters. And the number of repetition doesn't influence it that much. Same for the other parameters. And as you might have remembered, we can see that some parameters have a higher value of precision. So for instance, psi capital B small a. Then this is an ugly plot warning. I'm sorry, but this just means that we looked at the bias. So basically the difference between the estimation and the estimated values. I don't see any pattern. If you guys see any pattern, raise your hand, but I don't see any pattern here. So basically it means that the bias, it's pretty okay. So now what does it mean? The interaction scenarios didn't seem to influence the bias, but the precision. The repetitions didn't seem to affect the parameter estimation, but the number of sites seemed to have the bigger influence on the precision of estimations. And we had this parameter, psi capital B, capital A, more precise than psi capital B, small a. Now, to the surprising fact. We looked at the delta AIC, so the difference of AIC between the model accounting for interaction and the model not interacting for interaction. So in unmarked, it's just one small parameter that we decide to put at 0 or 1. So it's quite easy. So we compare this delta AIC. If the delta AIC is above 2, it means that the model accounting for interaction performs better than the one that does not. We looked at the proportion of simulations in which we had a better delta AIC above 2. And what we had was quite surprising. So it means that in most, if you look at this, this is the 50% line. Most of the scenarios fall under the 50% line. So it means that we have a minority of cases of simulation. Yes, 1 minute, thank you very much. In which the model accounting for interaction performs better than the model that does not, even though there's an interaction. Except in those cases here where we have 100 sites, and in the high type of interaction scenarios. So that was the surprising fact. And now, so to conclude, only in high interaction scenarios does the model accounting for interaction perform better than the one that does not. The number of sites helped get a better delta AIC above 2. And yeah, that's about it. Thank you very much.
Okay, getting mixed signals, but thank you, Julie. We have time for 1 or 2 questions. Oh, and there is one in the chat. Oh, yeah. So Chris Sutherland asks, have you tried with lower, more realistic detection probabilities? A very nice talk, by the way.
Oh, thank you. Actually, we stayed at the high probability because it was the best case scenario. We haven't tried yet with lower detection probabilities because we already had those surprising facts, but we think that it's going to be kind of in the similar trend, but that's definitely something to do, yeah.
All right, any other questions in the room? Yep.
Thanks for the talk. So like Chris was just saying, these seem to be like, or like you said also, these are best case scenarios. So do you think that means that very often then we're just assuming that or finding no interactions even though they're actually existing? Because that's basically what you were showing in the simulation, yeah?
So I think it's, well, so we kind of conducted a little literature study about studies that apply this type of models. And actually there was a lot of cases where they were not comparing with a null model, which is the one with no interaction. So I think that's quite something to mention, that actually it might be interesting to check in those studies how the AIC is doing before going straight for interactions when actually we don't know. So yeah, that was the interesting part. Yeah.
Great. Thank you again, Julie.
Thank you.
Our next speaker is Prashant Mahajan, talking about interactions and coexistence of canids in Western India.
Hello everyone, thanks so much for the introduction. So I'll just give a brief about the species interactions. So carnivore assemblages, including both meso and large carnivores, they can generate patterns of negative interactions known as interference competitions, however, which can result into a more serious interaction in some cases known as interbreed predations, which can reduce the fitness of a subordinate species. But also some large carnivores, they also have a positive interactions with some smaller carnivores. For example, they may provide the carry-on facilitation to the smaller species. Moreover, multi-species interacting with each other, they need, in a resource-limited environment, they can coexist by different ways. For example, they can partition in the way of using if there is a difference in diet, or there is a partition by spatial partitioning, or they can partition in temporal activity patterns. So in India, the semi-arid landscape and arid landscapes are traditionally been considered as wasteland. So therefore, there has been an increased anthropogenic activities in case of like there has been land conversions of into barren land to agriculture areas, and also there has been increased human activities, and due to overgrazing, there has been like really less available spaces for the species to like present there. So in a resource limited environment, there can be a high chances of negative interactions. So which can result in like they can result in more interactions, negative interactions between those competing species. So we considered the three candidate species, namely wolf, fox, and jackal. And also we considered the hyena. We considered the hyena because it has the same similar ecological requirements as those of those candidate species. So we conducted study in a western part of India in Ranthambore and the Kiradevi Wildlife Sanctuary, which is a part of a buffer zone of Ranthambore Tiger Reserve. It has a rich array of mammalian species, both carnivores and herbivores, and also it is surrounded by, like, it has 60 villages inside it. So it is highly anthropogenic in nature. So we divided the study area into 48 grids of 14.4 square kilometers, and in each grid we walked a trail of 4 to 6 to square 12 kilometer and recorded intact signs of scratch marks or pug marks of different candidate species. So for each of the kilometer walk, we considered 1 kilometer as a spatial replicate, in which we collected the zero and presence absence signs of each focal species. So we used two species co-occurrence patterns of beta psi BA parameterization of a single season, two species co-occurrence model. As the previous talks discussed before, they use the Rota et al. Method. But this is a method in which we considered that already there is a one dominating species, and the other species is a subordinate species. Rather than there is no. We don't like it's a beta BA parameterization already considered that one species is superior than the another. So it has the three occupancy estimates. The one is psi A, which is the occupancy probability for interacting species A, which is a dominant species. The other is psi BA, which is the occupancy probability of species B in the presence of species A, and the psi B small a, which is the occupancy probability of species B in the absence of species A. So we can put the psi B capital A and psi small B small a together equal to constant equal to together, which means that there is no interactions. Or we can put them individually, like estimate them separately, which means that they are interacting. So in this way, I build a 6 pairwise assessments, in which in one I can first consider the wolf as a dominant species with the jackal, hyena, and fox. And then in second, I considered the hyena as a dominant species with the jackal and fox, and I considered jackal as a dominating to fox. So I built 13 models for each of the pair species, in which the first 3 models were without any covariates, which include both the interacting models as well as without any interactions. And in the with covariates, there were 10 models, which 5 were with the interactions and the 5 were without interactions. I didn't include any interaction in the detection probability because we assumed that because we collected data on indirect signs, so we didn't want to add multiple parameters to avoid like to have the parsimony of the models. So the 2 species co-occurrence models were fitted in R using R presence package, and the probability of 2 species occurring together at a site is estimated by calculating species interaction factor. So when SIF is less than 1, it means that the subordinate species are avoiding the dominant species. When it is equal to 1, that means there is an independent occurrence. Both species are occurring independently without the influence of each other. When it is greater than 1, it means that the species, the subordinate species is favoring the species of apex predator or the dominant predator. So out of the 48 grades, wolves and jackal were recorded maximum in 37 grades, while fox was just recorded in 9 grades, and hyena was recorded in 43 grades. Out of pairwise assessments, hyena and jackal was maximum recorded in 23 grades, and jackal and fox were minimal recorded in 3 grids only. So these were the top models based on the AIC values and delta AIC less than 2. So most of the models, agriculture played an important role in the species interactions. And there were not many, like the top models for most of the interacting species were where there was no any interaction as such. For wolf and fox, the probability of the beta coefficient show that it has a agriculture value agriculture value has a negative influence on the habitat use of fox, while the agriculture has a positive influence on the habitat use of wolf. And the SIF was 1, which means that there was no any interaction between the wolf and fox. For wolf and jackal, in the presence of wolf, agriculture has a positive influence, while in the absence of wolf, it has a negative influence. However, the SIF was equal to 1, which again indicate that there was no any interaction between the wolf and jackal. In wolf and hyena, there was a hyena they support, although they inhabited the habitats which was occupied by the wolves, and they also, when the wolves were not occupying that habitat, they were also avoiding the agriculture areas. So SIF was greater than 1, which means that hyena was actually considering the areas where wolf was present, which may be due to the case that wolves may provide them carrion provisioning. So in jackal and fox also, fox avoided the areas where jackals was present, and also fox only was present in area where jackal was absent, which may be due to the case because jackal and fox, they both had similar ecological requirements, and they are often overlap in terms of their dietary and temporal partitioning, also space use. So also SIF was less than 1, which indicates that the fox was avoiding the areas that has high occupancy or habitat use probability of jackal. In hyena and fox also, there was no any interaction as such, because fox was not they were not avoiding, fox was not avoiding the areas that are in which hyena was present. In hyena and jackal, the jackal avoided the areas where hyena's probability was high. It may be due to the fact that hyena is larger in size, and also they have very much overlap among the resources. So hyena may provide more interference competition to the jackal. So these are the complex interactions. To sum up that for the hyena there was a positive interaction with that of wolf, while with the fox, fox has a negative interaction with jackal, and jackal has a negative interaction with hyena. So these values indicate the beta coefficient values of different covariates. So that habitat partitioning plays a very important role in the species coexistence. Different species, they occupy different habitats and respond to differently. Also, it is interesting to note that the body size of the species also a determining factor that what kind of interaction will be. If the body size, if there is an intermediate ratio between the subordinate species and the top carnivore species, then there will be a high chances of there will be negative interactions, because they have both similar requirements. If the ratio is too low, if it's too low, then it will be lethal for both of the species to interact simultaneously, because it can be lethal for both of the species. When the ratio is too high, it means that it won't be ecologically or energetically feasible for a carnivore to spend its energy, optimize its energy towards a smaller carnivore. So for most of the species, the ratios are intermediate. So only for jackal and fox, for hyena and jackal, it was intermediate, which also as results suggested that they both have the negative interactions. While for wolf and hyena, there was positive interactions, because wolf may provide the carrion subsidies to the hyena, and hyena is a scavenger in that landscape. So also our study has certain limitations, that we only consider the spatial overlap between the species. We didn't consider temporal pattern and dietary overlap, which might also be there, and there might also be other kinds of interactions based on the temporal and dietary overlaps. So we only consider the one spatial scale. The behavior patterns that are made under the risk of fear, they occur at a multiple scale, and it's important to determine at which scale the species is behaving. So we just consider one spatial scale. Also, the low density of competing species like the wolf, which was spotted only in 9 grids. So it might be possible that there might not be enough encounters, or the density is not that high that they will generate that kind of enough encounters between the species. Also, indirect signs, we collected data on indirect signs, which might influence the detection probability, but we didn't take into account because if we take all the parameters, so many parameters into account, it might not converge the models. So that's why these were the certain limitations. And thank you for your attention.
Thank you very much. We have time for one quick question.
Yes. Hey, thanks for the talk. So I'm a bit interested in this dynamic between the wolves and hyenas. You're assuming the wolves are dominating the hyenas, but do you have much actual behavioral observation?
No, I just collected data on the indirect signs only. So maybe if we deploy camera traps, or if we do a GPS collaring, then there will be fine scale interactions we might get. But these were just based on the indirect signs that were collected on the grids. So I observed that it suggested that because hyena is a scavenger, so it suggested that wolf may provide a carry-on facilitation to the hyenas. So yeah. Thank you.
Right. Thank you very much.
Thank you.
Again. Our next speaker is Matt Metz from the National Park Service, and he will be talking about estimating the abundance of wolf-killed prey using a marked recapture framework. Online? Okay, he's online.
Well, good afternoon. Well, I certainly wish I was there with you in person. I appreciate the opportunity provided by the organizers to remotely present our research focused on estimating the abundance of wolf-killed ungulates. So large carnivores killing ungulate prey often result in dramatic scenes such as this one. And these repeated events can dramatically affect ecosystem processes. So disentangling the effects of large carnivores and predicting predator-prey dynamics can of course be accomplished through many ways, but often involve estimating the abundance and characteristics of prey. Today, I will discuss our research focused on estimating the abundance of wolf kills within Yellowstone National Park, located in the northern Rocky Mountains of the United States. So outlined by the purple polygon is Yellowstone's northern range, defined by the historic wintering distribution of the northern range elk subpopulation. This is a key area within Yellowstone for large carnivores and their prey, especially during the winter. Much of the work I will present today indeed stems from data collected in this area. However, we collected data through wolf packs that generally lived within this red outlined space that extended beyond the northern range. And our focus was estimating the abundance of these packs' kills. These kills could have been any of 8 ungulate species. Here, 4 of the primary players are shown, with elk and bison being the most important across space and time. We specifically searched for wolf-killed ungulates over a 25-year period. And we did so for 408 different pack sessions, where a pack session simply indicated that we searched for a pack's kills over some consecutive period of time when we intended to work. These pack sessions occurred in early or late winter and were 30 days in their duration. So again, our goal was to estimate the abundance of a pack's kills for a 30-day period. But in reality, we estimated the abundance of all ungulates that they fed on, not just those that they killed, as wolves within our study system may also commonly scavenge, basically intact carcasses that die of causes other than wolf predation. So we searched for these carcasses in 3 independent ways: aerial and ground radio tracking and observation, and then searching clusters of wolf GPS locations. So what this would look like during a 30-day period is as follows. First, the plane had a daily flight in the morning, weather permitting, where we radio tracked all of our study packs. Next, ground teams radio tracked 2 to 3 wolf packs each day from dawn to dusk, with the hopes of observing them for as much of the day as possible. And finally, we also searched GPS clusters for 1 to 2 wolf packs. Note that the use of these methods has evolved through time. We began first independently recording carcass detections by each observation team. and then also added GPS cluster searches a little over a decade ago. And as can be inferred from the previous slides, not all pack sessions were monitored by all methods. Most, in fact, were monitored by only the plane. However, about a third included ground monitoring, and about 10% included GPS collars. So through this collective effort, we detected 2,500 carcasses over these 25 years. And for each carcass, we described its detection history over a 2-day carcass lifespan, where the NA indicates that a method did not operate for the associated pack during that 2-day window. Our goal, of course, was to turn our detected carcasses into an estimate that also included those that went undetected. So we estimated the abundance of carcasses through data augmentation, where we padded our observed data for each pack session with additional rows of all 0 detection histories. And our model included components that handled some key biological processes, detection probability, and availability, the latter of which allowed us to address that not all pack sessions were monitored with the same sampling effort. The first biological process that we accounted for was pack size, for which we hypothesized a positive effect, as it's well known that larger packs tend to feed more frequently. And additionally, we also included the potential key factors of prey size and seasonality, each of which we also expected to affect how many carcasses a wolf pack fed on. The next part of our model was the detection component. This part of our model was complicated in that we expected individual covariates to have effects on detection that may differ in their magnitude for each method. Moreover, we did not hypothesize that each detection method would be affected by every covariate. So in some cases, we excluded covariates for a method through using a dummy variable. For example, we expected distance to have a negative effect on detection, but only for the ground method. Conversely, we expected carcass size to affect detection for all methods and to do so in a positive manner. We also expected additional covariates, such as how open the landscape was, to sometimes affect detection. We then went about building our model to estimate the abundance of these sort of successful predation events through assessing whether the 90% credible intervals for relevant beta coefficients overlap 0. So here I will show you the coefficient estimates for both the process and detection parts of our model. What we ended up with looked very similar to what we hypothesized. First, for the process model, all of our hypothesized covariates were retained and had the predicted directional effect. For the detection part of the model, biomass and distance, which I highlighted during the methods, were also important with directional effects as predicted. The other covariates were also generally retained for relevant methods with effects as predicted. For example, the strong effect of viewshed, shown on the bottom, on ground detection was unsurprising when considered in the context of other previous work within our study system. In our case, however, we also still needed to account for variation in sampling effort. So here, availability described whether detection methods were operational for a pack session, which was affected by whether a method was employed, and if it was that method able to work? And what this plus displays is what we ended up using as the input for predicting whether a detection method was operational during each row of the augmented data. So first note that there is great variation in sampling effort for the airplane, which was caused by weather. For the other detection methods, however, they generally operated when employed for a pack session. So accounting for this variation in effort, primarily due to the sort of weather that is occurring as the ground team watches these wolves feed here, was a critical step to ultimately get us to our end goal of estimating carcass abundance. As then expected, the increase from our naive numbers, or what we detected, generally differed depending on how we monitored the pack session. In the case where we threw all detection methods at a pack, for example, we saw a little increase. Conversely, the increase is drastic for those pack sessions monitored by only the plane. And then the other monitoring situations fell between these extreme cases. So through our model, we increased our original 2,500 detected carcasses to about 5,700, or 2.3 times that what we originally detected. It's therefore easy to see that our model that accounted for detection probability and sampling effort was an essential step for estimating wolf predation metrics in our study system. Nonetheless, this estimate only provided the number of carcasses. But for the detected data, these carcasses are of course various species and sex age classes, not displayed here for simplicity. So maybe for a study session, it looks something like what I show here. And then for that same study session, perhaps we estimated these additional carcasses to be on the landscape. But at this point, we don't know anything about the demographic characteristics of these carcasses. So we therefore used additional detection models and information about the demographic characteristics of the prey that we did detect to predict the demography of these estimated carcasses. So doing so moves us towards being able to take our model results, which were born from the interactions and outcomes of events such as these, and leverage them in other ways. For example, we are working to develop predator-prey models to understand how it is that these events of predation and scavenging contribute to influencing predator and prey population dynamics. So with that, I'd like to thank you for your interest and attention, and then also acknowledge the people that provided the support for this work, including major funding sources and staff. Thank you.
Thank you very much, Matt. We have time for 2 questions. Perhaps first, can you hear us?
I can, thanks.
Excellent. Okay, time for 2 questions.
Hi, Matt, can you hear us okay?
I can.
Cool, thanks for your talk. This is Molly, by the way. I was just wondering, so you talked about this is an example from a national park, and I'm wondering if you think these methods could apply and how you would recommend trying to estimate, I guess, carcass abundance outside of a national park system.
Yeah, great question. I think outside of a national park, the methods for this particular question would still work. The key is that it really kind of informs us that GPS collars aren't perfect in this case, since that would be the method most often employed. Same thing would apply for a plane though, although funding would be the challenge generally.
I was curious if your method could be used to look at unsuccessful predation attempts so you could get a measure of foraging efficiency.
Yeah, it's a good question. I haven't really thought about it. I think it could eventually be integrated with models that are looking at interactions between predators and prey, and kind of look at the outcomes after those interactions to predict if there was a kill site there. But I haven't really thought about it. It's a good question. I'm not sure.
All right, thank you again, Matt.
Yeah, thank you.
And our last speaker in this session is Frédéric Bracon from the Institute of Mathematics of Bordeaux and the CNRS, and he'll be talking about the various concepts of independence in IPMs.
So thank you, Rachel. All right. So I'm not going to talk about species interactions. I'm going to talk about assumptions we make or don't make when we formulate integrated population model. So we've seen many integrated models in the conference, and an early paper from Bespeas and co-authors said that when we try to find the likelihood of an IPM by multiplying the likelihood of capture data times the likelihood of the capture count, we make an assumption of independence, which is actually not likely to be violated. But then partially the same set of co-authors found that it's sometimes the case that the census data and the demographic data are not independent, in the sense that if you study like mammals on a small island, the individuals that you count and the individuals that you mark will be the same. And they found doing a simulation as well that when they had what they call dependent census data, then they had basically lesser quality of fit. So this could appear even more worrying when we combine capture-recapture data and fecundity data, because we often definitely do that on the same individuals when we that this happens at the nest, for instance. So there's been a number of tests, simulation tests of that assumption of independence, and basically they all find that the violation of this independence assumption is not a problem. And so the question I'm posing here is the overlap between individuals that you use between the different data sets really violations of the assumptions? And to better understand that, we need to come back to what is probabilistic independence. So probabilistic independence is, if I want to compute the probability of A and B are two independent events, it will be the product of probability of A times probability of B, right? That's basic, and if you do this with random variables, it's the same. Now, physical independence is a different concept. It means like the physical entities on which you measure things are not the same. And those two concepts don't necessarily have to match. For instance, you can have probabilistic independence with physical dependence. If I just do a coin toss and I want the probability that it will come up heads, and then tomorrow I play dice and I want the probability to do a 6, and I want to compute the probability of this joint event, it would be 1/2 times 1/6. And yet I'm the same individual. So you're probably thinking like, nothing to do with capture-recapture, nothing to do with reproduction. So let's spice it up slightly. So let's say I draw a Bernoulli random variable on day 1, and then I draw a Poisson on day 2. And so the joint likelihood will look something like that, even though I'm the same individual. Let's now imagine that we are n individuals and we're all ducks, like we often do when formulating this type of models. So actually, let's say we draw a Poisson variable first, and then some of the individuals that reproduce survive or not survive. And so if you do that, the likelihood will look like this, except here you will have a product in red. And this product comes another independence concept, which is the fact that the individuals themselves are probabilistically independent, like individuals 1 and 2 are not more likely to get the same outcome set as 1 and 3. And here, because of commutativity of the product, you get a product of the component likelihood. Sorry, this is the old presentation. I thought I corrected this anyway. So you get probabilistic dependence of D1 and D2 in spite of complete physical dependence between them. Now, I'm not going to comment this, but it's just to say if you do it over a number of years, it would turn out exactly the same. And you probably say, wait, the models that we use, they are so much more complicated. There's these hidden latent states, etc. So let's say we have a Cormac-Shirley model in which we have a probability of detection and a survival probability. And so our observed histories are X and latent state is Z. And we have Poisson fecundities when we manage to observe the individuals. Now, the joint likelihood, and I hope you trust me on this, becomes this. So actually, there should be, this here should be conditional to the observation. Sorry, I thought I had corrected this, but apparently I didn't. Oh, this is the old pronunciation. So in blue, this is the probability of capture and reproduction, like the joint capture and reproduction history for a given individual. And so it includes both X and Y data. And then you have to sum over all the latent state, and then you take the product
of the probabilities for all individuals, given that you assume that by default they're all independent in the simplest models. And if you play around a little bit with this, you will have the reproduction data. So there's a X, knowing X here term that's missing that will come out here. And by simplifying progressively, you will end up saying that this is the likelihood of the capture-recapture data times the likelihood of the reproduction data. And so here you have all capture, recapture, and reproduction measures that are done on the exact same individuals, and yet the likelihood will write out as a product of the likelihood for the two kinds of data. So of course, these are the simplest models, and you can obtain dependence between the probabilistic dependence between the data sets if you have, say, physiological trade-offs, like if you reproduce well this year, next year you will have bad survival, or if there's any kind of structure in the population, so genetic structure, any kind of heterogeneity, which would make individuals belong to different clusters. But in a way, this is not what has been studied in most of these publications that have evaluated the effect of physical dependence between data sets, right? These are the things that can generate probabilistic dependence in the data set, but this is not what has been evaluated so far as I know. So actually, you can also build IPMs without this probabilistic independence assumption, and you're not restricted to this. And every density-dependent models, for instance, you have the counts that are used as a conditional for the capture-recapture data. For instance, if you have survival that depends on population size, then it needs to be dependent on the counts. And actually, when people do this in a Bayesian or /MCMC setup, you don't have to use these products that you would need to do maximum likelihood. So we are not restricted at all to the same using different individuals for different data sets, and even using the probabilistic independence assumption. But there's a larger issue, which is how often does the full likelihood formulated at the individual level match the product of the different component likelihoods for the different data sets. So as take-home message, I would like to say that probabilistic independence of data set is not equivalent to physical independence of data sets, that the full individual-based likelihood can at times be simplified to a product of component likelihoods in the simplest models, even though the measures are done in the exact same individuals. And of course, there are some mechanisms that can generate probabilistic dependence between data sets, but they are in more complex models in which you have more complex structures. And you can fit IPMs without independence between data sets. And my take-home message is that writing down models, trying to write down models to the individual level can help to clarify what these models assume or not.
All right, thank you. We have time for one question. Please, somebody, don't leave the hardest one to me. Right in the back there.
Thank you for a very interesting talk. This is perhaps a naive or misguided question, but I'm wondering has there been a confusion between the notion of independence and the notion of conditional independence, conditioned on like the latent state of the population? Is that account for for this, or do you think that's not coming into things here?
So there's probably a confusion. There's definitely a confusion between physical independence and probabilistic independence. Also, it's a little bit fuzzy on whether people use in the papers like full independence or conditional independence. Like, is your model on reproduction conditional to the counts or unconditional to the counts? Often that's a bit fuzzy in many articles.
Great, thank you very much again, and thanks to all the speakers of the session.
Good luck on short web.
Presentations. Thank you.
Yeah.
I think I want to see more.
Yeah.
Occasionally say.
That's The group is huge and doing great things. Perhaps I should come visit you guys sometime. Just good connotation. Of course, you're always welcome. So it's cool. Yeah, this is cool. Actually, nice to try and work on that. Especially because that was so many yes, question. So let's definitely come up with this. He followed up on LinkedIn and say, that's really interesting. Social
Oh, he was great. One
Maybe I don't think so.
I'm managing the C'était une idée à l'idée des fortes
Okay, welcome back. We'll start the final session of the day. So our topic is species movements, life history, and detectability. Our first speaker is Casper Thorup, who's recorded his talk speaking on historical changes in migration patterns.
Hi, and welcome everybody. I'm Casper, and I will talk about historical changes in migration patterns. And let's see what we have in the bag here. Lots of long-tailed tits flying out to be recovered. And I hope you have maybe had a chance to look into this webpage, the recently published Eurasian African Bird Migration Atlas, covering recoveries of all the birds ringed across Europe. And here is shown, for instance, for species like barn swallow, very many recoveries showing how different populations go different places, and also simply how many birds have actually been marked. Here I have shown the variation over time in both in all the recoveries, and also focusing on the birds that have been ringed during breeding and recovered during winter, the subsets that we will focus quite a bit on here in this presentation. But before we look further into how this can be used to look at changes over time, I would like to go back to Hans Christian Mortensen's storks, the founder of modern ringing, and he ringed a lot of storks and got 88 recoveries, and you can see quite clearly that these birds are migrating southeast to and down then to southern Africa. And if we now look go forward in time and look how has this changed since, it's quite clear that recoveries after 1970 are more to the southwest, and also shorter distances, mainly wintering in the Iberian Peninsula compared to those before 1970 that quite clearly confirm that's the same migration pattern as what Mortensen originally observed. And if we look at the European data, it's quite clear that the western part of the population has started to move much more towards the Iberian southwest, towards the Iberian Peninsula, and also going shorter distances than before. You can see the average is shown here for the last 3 decades. It's much shorter than it was in the early days. And this is also reflected here, simply plotting the recoveries, that the latitudes are becoming more northerly, a larger proportion of birds are staying or recovered within 100 kilometers from where they were ringed, and the longitudes are getting more westerly, and migration distances or distances between ringing and recovery are generally getting shorter. But if we look at a species here like black kites, it become a little more difficult to interpret the patterns. There are some recoveries north of the Sahara and some south, and it's indicating that there are no clear changes, but this might of course be influenced by changes in recovery probability. And one of the ways that has been looked at recovery probability, spatial variation in recovery probability, is this way of comparing here kestrels and buzzards. There are very many recoveries here in Europe, but if you look at a species like black kite, there are not very many recoveries here in Europe, but there are some in sub-Saharan Africa, and likely quite a larger bit of the population is actually migrating, indicated by the very few recoveries north of the Sahara. In general, we have 2 overall challenges that we had to try to solve when looking at changes over time in the European ringing data here. And challenge one was that ringing and marking data are generally missing, so only specific cases has it proved possible to actually acquire this data. But for the vast majority, we don't have it yet. The other challenge number 2, is that recovery probability and mortality are confounded, and especially, and we're looking at changes over time. If one of them is changing, it might affect how we estimate the other one. So that's also needs to somehow be looked into. But one of the ways that we try to get around these challenges is to group species into groups where it can be considered likely that they are overall similar, these parameters. For instance, seabirds and gull having generally comparable mortalities and comparable recovery probabilities, similar also with passerines, where they're much lower. Both the mortality and, mortality is higher and the recovery probability is lower, but that's probably a similar in these species. So the first approach we have used, we compare different latitudinal bands here, 10 degrees north, 20 degrees north, and 30 degrees north here, and that's comparing a migrant and a resident. And here I show an example of how the calculations have been done. If we look first in the first decade here, the migrants are all recovered in the southernmost parts, whereas the resident has been recovered in those 2 more northerly parts. If we now look at decade 2, there's been a change here for the migrants, so a few more migrants have been recovered a bit further to the north. And if we now compare the proportional of migrants and residents in each of these latitudes, 80% of this latitude, of the recoveries at this latitude, are migrants. And if we then correct for this, the sum of these proportional latitudes, then we get an weighted latitude here, and that sums up to latitude, an average latitude corrected for these proportions differing between the migrants and the residents. Using this method, we get rather similar results for the wintering latitude than as what was simply the data gave for the wintering latitude. There is slightly less clear pattern, which could reflect that actually some of these changes are not due to real changes in wintering latitude, but to changes in recovery probability. We also used another method for trying to estimate these recovery probability, this spatiotemporal variation, and it's somewhat similar to the method that Francie and co-workers used here to estimate the numbers of common nightingales ringed, simply based on the recoveries during breeding, and which was taken as reflecting the numbers ringed. So we applied some similar assumptions here. I'll show an example of how this was done. Recoveries north and south of the Sahara here, and that's north and south of 25 degrees. And here, if we look at, we compare the total recoveries with those recoveries of birds during winter that was ringed during breeding. And you can see here there is a 50% chance of getting one of those recovered compared to the total number of recoveries. And if we now look in the migrant here and compare, then if the likelihood of recoveries for those staying is 50%, then we can assume that 20% of the total population are actually likely to be staying. That's the best estimate of fidelity in this migrant. If we now look at the decade number 2, there is one more recovered south of the Sahara, but this doesn't affect the fidelity estimate, simply because the likelihood of this one is determining it. So this might well be because there is a higher reporting rate or higher likelihood of recovery in the second decade. If we look at the third decade here, we do see a change, even though these numbers are similar, and this change in estimated fidelity is based on a change in the resident, where we suddenly have a higher probability of actually getting one of these breeding winter recoveries. So with this method, we get slightly less clear pattern for the white stork. We still see a clear change in that more birds are staying, but otherwise we mainly get results for seabirds, not so much for other species. And these are in the general positive, meaning that birds are more likely to be resident than or staying closer than they were before. Anyways, there might be quite some influence of different populations changing differently. So even though we have many different new methods, I still think the ringing recoveries are important, and these birds are being ringed and recovered. So I hope that we can extend these methods so that we will get perhaps be able to look more into detail with different populations as such. So with that, I wish you a great conference, and thanks for now.
Welcome, Casper. Do we have questions from the audience? If not, I'll jump in with a question. This is Brett Sandercock. Is there any possibility of using the information on cause of mortality for the ring recoveries? For example, in the stork example, if it's apparent shift in migration orientation, is that due to more risk of mortality from collisions with power lines or wind energy infrastructure?
Very relevant question. And well, sorry, can you hear what I'm saying?
Yes, we can hear you.
Okay, that's great. That's a very, very relevant question and comment. And there are actually so many possibilities that it's really, really hard to look at each of them. So the main, this has not been taken as a main analysis, part of the analysis, but yes, it surely can be extended into that for individual species. I guess that's sort of this is hard when you are looking at all the species together, but for individual species, I'm sure a lot of this can be extended.
Thank you. We have time for one more question. If there's a question from the floor. Okay, thank you very much, Casper, and hope you can join us at the next Euring conference.
Yeah, thank you.
So our next speaker is Jacob Davies, speaking on quantitative year-round modeling of the movements of European waterfowl populations.
Hi everybody, I'm Jacob. I'm here from the BTO and I'm going to talk about quantifying European waterfowl movements. So this work arose out of concern about avian influenza and domestic poultry. So AI is a massive threat to domestic poultry. Tens of millions of poultry are killed every year due to this disease. And wild birds, especially waterfowl, play quite a big role in, well, some role in HPAI transmission between poultry flocks, particularly over long distances. So this raises the question, can we use typical waterfowl movement patterns to predict locations of outbreaks? So this was part of a wider project for EFSA to develop a prototype early warning system for AI and the EU. I'm not really going to go into the wider project here, but you can read about it online in the report to EFSA. But the aim for our part of the work was to use Euring ring recovery data to quantify waterfowl movements between locations in Europe. And this kind of draws on some earlier work for the migration mapping tool. So the data we used were Euring ring recovery data for 2 species of swan, 5 species of goose, and 5 species of duck. And altogether, so we used all ring recovery records, so birds were encountered dead or alive. And this came to more than 1 million ring recovery records, which sounds like a lot, but nearly half of them were mute swan. So for example, and only 7,000 were pink-footed goose, so quite a spread between species. So the target parameter we were after here was the proportion of individuals moving between a given origin location and a given destination location between consecutive months. So we were really trying to capture long distance migration and cold weather movements with this parameter. So for example, if we had an origin location of Northern Finnmark and a destination location of Denmark and a month pair of September and October, we want to know the proportion of mallards that were in Northern Finland in September and then found in Denmark in October. And for example, if we had an origin of England, it would be the same quantity for there. And we'd also want to know this for Denmark itself. So what proportion of mallards in Denmark remain there over that month pair. And in fact, we want to know this for all origin locations. So how do we go about finding this? So the data that we used were, for this example, all mallard movements from September to October. We then categorized them by whether they did move to this 500-kilometer cell or not. And it's a little bit hard to see where these birds came from, but if you plot them by their origin location in September, you can see that these are the birds found in Denmark were mostly birds that were already there in September. But also you got some birds coming down from kind of the northeast from Fennoscandia in September. And then we would use these data to construct a variable, so a binary variable, so whether or not birds made this movement. And then we would just fit a spatial surface through those data to estimate this parameter, our target parameter, the proportion of birds making this movement for this month pair. And we fitted the spatial surface because we expect I suppose we expect this quantity to vary smoothly over space. Sorry, got my order wrong here. But also it allowed us to share information between origin cells because you can see that quite often there's gaps between where we have information for movements, and I'll come on to that in a bit. And also just for the actual product that we need to supply to the epidemiological model, we needed estimates for all origin cells. So this is it's a bit hard to see the surface behind the dots here, but you can see that it's kind of, this probability is quite high around Denmark, and then also it's estimating it to be relatively high in northeast Fennoscandia. And we fitted this model in lab because it's really fast and good for these big spatial models. So we would run this for every month pair. So here's December to January to here. So this time of the year, they're quite stationary, and it's generally quite a sedentary species, so there's not that much movement. But you can see that in kind of late winter, birds are moving up to Denmark from France, and then sedentary over the summer, and then you've got some kind of return passage from the north in late autumn. And then we would do this across months, across cells, and then across all species. So this worked in some situations. So here's an example of where it gave plausible estimates. So if we're looking at the proportion of Hooper swan moving to northern Britain in kind of late autumn to the winter, that proportion is estimated to be quite high in Iceland and northern Britain, but not in Europe. And then the opposite is true for a cell centered on northern Germany. So it's estimating the proportion of birds moving there to be high in Poland and the Baltics, but not in the UK. So it's kind of separating out these two flyways. And then you kind of get here's another example for spring movement for pink-footed goose. So it's kind of giving a plausible kind of origin location for birds with a destination cell of northern central Norway. In the spring, birds generally moving up from southern Scandinavia, but not from the UK. But as we all know, I mean, there's some pretty stark issues with taking these movement estimates based on raw ring recoveries at face value. So one of the first issues is that we generally, or quite often, had too few data to generate movement estimates. So this is kind of a map of data availability, and it was relatively good in Western Europe, but quite poor in other areas. And particularly in Eastern Europe, there's a kind of a big disparity between the presence of birds and the available data. So the effect that this would have would mean that you would underestimate this probability or kind of proportion of birds moving to a location, or it would give like a really patchy surface where it's just driven by a few movements. Another big issue, as we heard from Casper, is just the kind of spatial bias in ringing and recovery effort. So these ring recovery data are generated by many different observation processes. So you've got ringing, hunting, recovery of dead birds, resighting, all of which vary spatially in different ways over the area. So that means that not all movements are equally observable. And so this had the effect of sometimes you kind of bias this proportion really high. So it looks here like in autumn, pretty much every single widgeon in Europe goes to the Low Countries and Eastern England, which we know not to be true. So this has kind of been a first phase in terms of just kind of creating this prototype model, but now we need to address these various data issues that are here. So firstly, in terms of increasing the size of the data set, we can incorporate ring recovery data from non-consecutive months. So we focused on consecutive months for the model. We can perhaps incorporate data of other forms, so perhaps tracking data, maybe use some of those for validation as well, which is going to be important. And then in terms of spatial bias in ring recovery effort, we can perhaps estimate the recovery probability directly, drawing on Franti and others' work from the past, or we can inform the model with external data sets, say on ringing effort. So currently, ringing totals are not collated across Europe at the moment, but that could be done. Or we can pull in data that might co-vary with recovery effort, so hunting effort, etc. But even though we know that these the absolute movement estimates are biased, perhaps the spatial bias is similar between species. And so if we derive relative movement estimates by comparing these surfaces, then perhaps the spatial bias will cancel out. So I don't really have time here, but I'm just going to trail some kind of provisional analyses we've done. So this is looking at similarity of long distance migratory origin between species. And you can see that it's generally quite low across species in terms of where they've come from. But you get species are generally similar in where they've originated in northern Britain and Iceland. And so perhaps you could use these data to kind of empirically derive flyways, multi-species flyways. And I'm not going to cover that, it's not time. But so just to summarize, this is a first step towards quantifying wildfire movement in Europe, spatially and temporally. I didn't really touch on it, but the epidemiological model was quite promising in terms of its ability to post-dix AI spread from known outbreaks. We believe that there are solutions to the obvious challenges in the data. And in the meantime, we think that relative movement indices might give us some insight before we can improve the absolute movement estimates. So I'd like to thank co-authors and funders, thank people that contribute to these massive ring recovery data sets, and thank you for listening.
We have time for one question.
Thanks for that. I was wondering how much your spatial surface would depend on the choice of grid that you use.
Yeah, so probably not much. Well, I mean, do you mean the destination grid or the origin grid? Because what we estimate when we fit the spatial surface is it's just a continuous spatial surface, but you kind of the predictions that you draw from it, the kind of more the more detail, spatial detail you have on that, the longer it takes. So that's the only real kind of cost to generating a really kind of small, kind of fine grid. But the destination cell grid, I guess we kind of use that as a trade-off between kind of computation time, amount of data within the grid. But yeah, I think we'd probably get slightly different results based on the grid size we use.
Thanks.
Thank you, Jacob.
Thanks.
Our next speaker is Emmanuel Adabija, speaking on testing avian body size conformity to Bergman's and Allen's rule along a latitudinal gradient. We don't have this one? Okay. Sorry, so we move on to Christophe Botella. Christophe Botella, okay. A dynamic species distribution model fitted to heterogeneous occurrences explains a plant invasion trajectory.
Hello, everyone. Today, I would like to present you a study that has been published last year dealing with a dynamic species distribution model fitted to heterogeneous occurrences, notably from crowdsourcing, that helped us explain and reconstruct a plant invasion trajectory in South Africa. I have done this work in Stellenbosch University, but also in collaboration with the PlantNet team here in Montpellier. As you may already know, biological invasion overall induce major biodiversity losses and also cost to human society. As for instance, in Europe, over 40 years, they have cost around $140 billion. It is important to better understand the processes that determine this invasion success if we want to better anticipate invasions and act timely and effectively. Our approach has been to connect mechanistic models to the past data on invasion at large scale. And for that purpose, we designed a state space Bayesian hierarchical model, also called sometimes as statistical mechanistic model. It is composed of a deterministic spatial population dynamics model, which determine the hidden population states, which are observed based on a statistical model of the observation process, here modeling opportunistic presence-only data in several datasets. There has been past examples of comparable models. For instance, in 2007, Cook and colleagues reconstructed the invasion dynamics of Heracleon Manteganism in the UK. And more recently, Louvrier and colleague reconstructed the recolonization of wolf in France. What I find interesting with this kind of model is that they enable interpretations, ecological interpretation that are consistent with past invasion evidence at large scale, and not only with controlled experiments. More specifically, we wanted to address two types of questions regarding the invasion dynamics. We already know that long-distance dispersal is crucial in determining the overall invasion speed, but the role of human activity in long-distance dispersal is still debated. And we wanted to investigate the role of age-dependent fecundity, specifically in woody plants, which have a huge scaling of fecundity with age, and its role in determining the life phase of the invasion. So for this purpose, we designed a state space model whose population process is hidden, not directly observed, and is composed of a model for the first year population states, decomposed per spatial cell and per life stages. We also model the transition function, which is composed of a model for the age structure fecundity, including the age of reproductive maturity as a parameter, the allometric scaling factor, and a saturation of fecundity at a certain age. We also model independently with two dedicated parameters, the rate of spread in neighboring cells at short distance and the rate of spread at long distance conditioned to the urban land cover to model the dependence to humans for long distance dispersal. We model the self-regulation with a carrying capacity that is modulated locally based on environmental covariates, including land cover and bioclimatic factors. And we model mortality as constant in space and time. So this is not a very original spatial dynamics model, but the more original part is the modeling of the data, which is opportunistic presence-only data, modeled as counts with a Poisson distribution whose intensity depends on the hidden population state in the cell and year, multiplied by sampling efforts, which is composed of the number of occurrences observed in this cell and year and for a given data set, modulated by a detection rate, which is a parameter of the model, and which accounts for the fact that certain data sets have less detection intensity for the species compared to other data sets. So in this study, we have combined 3 data sets, old and new, that together cover well the whole time period. So this includes the records from various herbarium across South Africa, centralized in the Bodatsa datasets, the records from the professional monitoring scheme of Sapia, which is dedicated for plant invasions, but it has been less active over the past years. But this is compensated by the crowdsourcing records from iNaturalist, which have exploded over the past 5 years. We took as a use case the plant Plectranthus barbatus, which is a bush introduced around the middle of the past century. And it is quite an impactful invasive species because it forms dense monospecific stems like you can see on the picture, which cover the existing vegetation. By fitting our model on the data of this species, we could estimate the local initial population back in 1980, the first year of our modeling, but also look at the age structure of the initial population. Besides, we could compare the relative population per cell and per year, as you can see on the figure on the bottom, or look at invasion syndromes, like the cells that were source population and the ones that were sink population. To synthesize our results, basically we have observed a massive and early long-distance spread wave propagated by humans in the absence of other long-distance disperser. We have seen, as you can see on the log population graph on the right, that the population has saturated around 96 and has remained constant after that. This delay in the population growth is partly due to the age dependence of fecundity, with an estimated age of reproductive maturity at 3 years. And this means that the lag phase posterior to the introduction lasted for more than 40 years. We investigated the importance of long-distance dispersal by removing this process in the model and resimulating the whole invasion. What we observed in this case, and is shown with the curve in red in the graph on the right, is the relative decrease in population in this alternative scenario compared to the reference scenario, led to a huge decrease in the population that has not been filled up to 2021. The more high-level take-home messages of this study are that if you combine opportunistic presence-only data with a control for sampling biases, you can actually get information, mainly relying on the range extension and the occurrence rate. Also, the use of spatial dynamic modeling enables to investigate alternative management scenarios that indicate leverages for dealing with invasive species. Still, we have to interpret the absolute values of the parameters with care, as we have some identifiability issues like the confusion between population size and detection rates. Also, the model convergence was difficult, and we still lack a proper way of accounting for the stochasticity of ecological process itself. This type of modeling will be the topic of a continued collaboration with Stellenbosch University, while I just began a new postdoc here in the PlantNet team in Montpellier. So we are pretty excited about it, especially investigating the identifiability issues, but also how we could use these models to investigate future invasion scenarios and management actions. And this will be the topic of synthesis that has been started. We're also excited about combining this type of presence-only data with more standardized data like presence absence and local counts derived from roadside pictures. Thanks a lot for your attention.
Welcome, Christophe. There are questions from the audience?
Thank you.
So the new spatial models that you developed, does that help with understanding the routes that the invasive plants are coming in, or perhaps identifying sensitive habitats that might be at risk?
So this was the idea, and what we found were that the cities were drastically important for the introduction of the species, and especially the introduction pressure. So the populations in the cities back 40 years ago were quite big, more than expected, and that from these cities it stimulated the long-distance dispersal wave. We don't know about the processes, and we relied on some assumptions about the initial states of the population and their distribution. So we cannot tell much more at this stage.
Any questions from the floor? Okay, thank you very much for your contribution.
Thank you.
Next, we have Brandon Edwards speaking on estimating land bird detectability from autonomous recording unit data.
All right. Yeah, jumped the gun a little bit there earlier, so good start, but oh, here we go. So yeah, hi everyone. Thanks for having me here. I want to start by thanking some of my co-authors here and some of the funders as well. So this is actually, I'm based at Carleton University, but this was actually a project that I undertook as part of a research visit at the University of Alberta and the Alberta Biodiversity Monitoring Institute. So I'm very grateful for their funding and their resources to help me out with this project. So yeah, I feel like I'm lucky in that I don't have to explain to this crowd the importance of detectability. So that certainly makes my life easier right now. Just as some quick things, I am interested in using detectability for things like correcting systematic biases in surveys, so things like roadside surveys, estimating population sizes, and then thinking about when to monitor species versus when to actually act on declining species. And in North America, we actually just published the first round of results for this large multi-agency project called NAPOPs. So that's a project that has been seeking to produce detectability offsets for ideally all North American land birds. In this first round, we did 338. So this is just like an example. So we have like things like availability as a function of day of the year and time of the day, and then perceptibility as a function of like roadside status and forest coverage. So yeah, and when I'm talking about detectability, I'm referring to the components that I think of. So things like availability, so the probability that a bird actually sings. And you can estimate that using things like removal sampling, and then the perceptibility, so the probability that if a bird is singing that we can actually hear the bird. So you can estimate that with things like distance sampling methods. Now, one of the problems, especially with bird sampling and trying to listen for auditory cues, as one of my collaborators, Aaron Bain, likes to always say, humans suck at estimating distance. So if I'm out in the forest and there's a bird singing somewhere in the forest, I can take my best guess as to how far away that bird is. And likely I'm going to bin that anyway. But whether it's like 48 meters or 75 meters, I'm going to take my best guess, but I'm probably going to get it wrong for the most part. There was the talk yesterday where, they flushed the birds using the dogs. So, maybe we could consider doing that. But otherwise, we're trying to do it with auditory cues. So we're probably going to get it wrong there. So we can maybe consider start looking at alternative technologies for collecting these data as well. So one example are these autonomous recording units, or ARUs, which I'm going to refer to. So in case you're not familiar with them, essentially how they work is we have this recorder that we put out in the forest or wherever we want to sample. And a happy little bird comes along and starts singing. If that recorder is on at that point, so actually recording sounds, it'll pick up that bird, and then later on we can transcribe it into something like a spectrogram, which I'll show you more in a second. And in North America, ARU data are thankfully widely available and starting to become even more and more available. So Alberta Biodiversity Monitoring Institute has this Wild Tracks website where a bunch of the ARU data from different agencies across North America are being uploaded onto this website, and you can access them and some of the detections and whatnot on there. So very handy website. So I asked, and kind of we'll show here, can we derive detectability estimates? And I say QPAD detectability estimates. That's just like a flexible way of estimating the components of detectability. Can we derive QPAD detectability estimates from autonomous recording unit data? So what do we actually need from these data then in order to try to estimate these detection probabilities? So if we have a spectrogram from an ARU data, On the x-axis, where's the little laser here? There we go. On the x-axis, we have like time, so like the time a bird is singing. Y-axis is the frequency of the sound from the bird, so like low frequency and high frequency. And then the intensity of like the colors on here is essentially how loud the bird is. So this is from an oven bird, so you can kind of see like the teacher, 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 teacher type song that they make. So, you know, if we wanted to think about availability, think about time to first cue, it should be relatively easy, right? Like we have the time on here, so that should be fine to get. Or is it? Unfortunately, for the purpose of this talk, I don't have time to really get into the nuances of it, but certainly ask me about it later, and I'm happy to talk your ear off about it. But the distance to the bird, if we just have a spectrogram, how the heck do you get that? Because if I'm out in the field, I can at least try to estimate the distance to the bird using things like landmarks, especially if it's like an open environment, I can use landmarks and whatnot. But if it's just a spectrogram, how do I get the distance to the bird? Well, we can turn to sound physics to try to help us out here. So suppose we had a recorder and we had two equal birds singing two equal songs. The bird that's closest to the recorder is going to be perceived as the louder bird than the bird that's further away from the recorder. And that's just because sound intensity, so the loudness of the sound, decays with distance. Similarly, if we have these two birds that start singing at the exact same time, the bird that's closer to the recorder is going to actually, you know, the sound waves are going to hit the recorder before the bird that's further away from the recorder. And this is just because, you know, sounds from farther sources take longer to reach the recorder. So just based on the speed of sound. So we have this idea of time of arrival from the sound waves and then the sound intensity. So if we strategically set up these recording units in a grid, for example, then maybe if we have a bird singing sort of in the middle of this grid, we can assume that, you know, this bird will be singing, the sound will likely hit this recorder first, maybe this recorder second, so the next closest recorder, then the next closest recorder, and so on and so forth. So we can use this idea of the sound intensity decay to figure out how far away from each of the recorders it is, and then using the, you know, the time to arrival of this sound wave, we can maybe try to figure out how, you know, where this bird is in this array of ARUs. And that's this localization technique that I point out here. Happy to chat more about that and go into the details, but yeah, that's what it is. So I'll give you just a few, like an example. The bioacoustics unit out of the University of Alberta have a bunch of these grids set up in Alberta. So they've been doing this type of data collection for a while now. So I accessed like 7 terabytes of their sound data, and I severely underestimated the data wrangling portion of this. So unfortunately, I have very little results for you, but I do have some like pretty looking grids in a second. So this is just one of the grid examples. So it's like a 5x3 array of ARUs. I think they're spaced about 50 meters apart or so. And so we can, you know, if we have a detection, we can make this grid of spectrograms. So this is the oven bird again. This spectrogram looks to be the darkest, you know, the most intense sound. So probably the bird is going to be around here, and then you can see that it fades out around there. So I might use these spectrograms in this localization exercise. So there's this nifty R package called Locar, I don't really know, that does this localization for you. So I use that, and so you get something that kind of looks like this. So this point here is where the bird was calculated to be, and so you can kind of see, you know, it's closest to this ARU here, next closest to that one, so on and so forth. There's a bit of like multi-modality going on here, so, you know, I could try to rerun that localization maybe with a smaller snippet of that sound wave, but overall this isn't bad. So from here, we can get things like distance to each of those recorders. And what I was hoping to be able to do for this Euring talk, and didn't have the time, sorry, is then model that known distance, or the estimated distance at least, versus amplitude. So if you have like amplitude on the x-axis and the distance, estimated distance on the y-axis, you can create these sound pressure level curves and then use these sound pressure level curves to then estimate distance for any other ARU data. So it doesn't necessarily have to be in that grid. You can just take any sort of ARU data, as long as you have the amplitude of that singing bird and this sound pressure level curve, then you can estimate distance to that bird. So stay tuned to the proceedings, I guess, and we'll see if that works out. So just as a quick recap for the localization, we're essentially going to estimate the distance to the bird using that localization method. Then we're going to generate the sound pressure level curves for that given species, and then use those sound pressure level curves to then estimate distance for any ARU recording, not necessarily just the ones in the grid. So just to quickly wrap up, why bother doing something like this? Well, ARUs are, very much a growing technology. So this would hopefully provide a new method of working with ARU data and a new workflow for working with ARU data. Especially in Canada's boreal forest, it's a severely undersampled area for traditional human point counts. You got to fly people in there to try to survey, but that's where most of Canada's birds breed. So it's a very important place. So these ARU things can fill in data gaps in Canada's boreal forest. And then finally, we can try to use this ARU data to improve estimates of previous detectability estimates that this NAPOPS project had initially created. So by augmenting this ARU data with the traditional point count data, and hopefully getting some better estimates for species already modeled or new estimates for species not yet modeled. So yeah, anyway, that's all I have to say. So thanks.
Questions?
Thanks. Sounds like a really interesting approach, and thanks for an interesting presentation. I was just wondering, are weather conditions likely to affect these sorts of estimates? Certainly they would do for humans in terms of changing the distance parameters.
Yeah, definitely. So one of the parameters that you can actually change around in this, I'm just going to call it LOCAR. This LOCAR package is the temperature. So that's going to be definitely one of the things that's going to affect how the sound travels. So generally, when they set up these ARUs, they have these sensors, and if not, then you can check like historical weather data to figure out the temperature at that point. So you can input that as well. Otherwise, they use like a default of like 15 degrees Celsius, I think it is. But yeah, otherwise, like other weather conditions as well, such as wind or just general, I guess wind is mostly the noisiest, would definitely affect it as well.
Brandon, the time of arrival calculations would require fairly tight synchronization among the ARUs. So what's the approach for that? I mean, usually they're all connected to one recording device.
Yeah, so they have I think it's like a GPS calibrated clock that when, I can't remember the exact specifics of it now, but yeah, it's either a GPS specific clock that controls the entire grid of ARUs, or I think they might use a cell phone or something as well. But yeah, they have it so that all of the ARUs start at exactly the same time, plus or minus maybe a few milliseconds, but ideally exactly at the same time. And then yeah, that's how they're all synced up. I'll check into exactly how that works because I can't remember off the top of my head right now, but yeah.
Okay, thanks very much.
Yeah, thank you.
Okay, our last speaker for the session is Gonzalo Perez on decline in avian detection more evident than secondary forest colonization in a 30-year-old Amazon forest disturbance frontier. It's a recording.
Thank you.
Sorry.
Good afternoon. I would like to share with you the results of an empirical study that was purposefully designed for analysis with a multi-species occupancy dynamics model. This study aims to compare use of Amazon old growth and secondary forest sites by understory birds, and we expected to find a stable baseline in the old growth and the increasing occupancy in secondary forests due to gradual colonization of the regenerating habitat. What I am sharing today is also the story of an unfulfilled expectation from which we hope to learn something useful. Pardon me for the mutation on this slide up there. The forest of our study area was partially cleared in the late 1970s, and this clearing facilitated the establishment of the Biological Dynamics of Forest Fragments project, which aimed to settle the old single large or several small controversy by monitoring experimentally isolated forest patches. This project started out as a press perturbation experiment, but with the unplanned abandonment of cleared areas by ranchers, became a pulse perturbation experiment in denial on a large scale, but with a smaller sample size, with a rather small sample size. You can see here the patches indicated in white, the remaining cleared areas in red, the surrounding old growth in dark green, and the recovering secondary forest in light green. When I moved to Manaus in 2004, almost all the cleared area had secondary forest. There seemed to be then much more potential for understanding bird population dynamics by comparing vast old growth and secondary forest areas than by sticking to the few poorly isolated patches. For this reason, we established a sampling design with 150 sites all over the project area, 1/3 of which were in secondary forest. Since it would be impossible to send observers to every site with sufficient frequency, we sampled with autonomous recording units. This work resulted in almost 11,000 hours of audio collected between 2010 and 2014. Each site was sampled at least 5 days per year and 3 hours per day. Ulisses Camargo, one of our co-authors, subsequently developed identifier algorithms for 62 of the nearly 200 species present in the recordings. We consider that a species was detected by one of the 3-hour samples when Ulysses reported that at least 1 minute in that sample of 3 hours had a higher than 0.9 probability of containing a vocalization of the target species. Here is Sandra Freitas in 2010 deploying a recorder in the field. What we want to infer for each species and for an ideal set of species that they represent is the probability phi with which a site that is used or occupied in year t persists occupied in year t plus 1. And the probability gamma with which a site that is not occupied in year t becomes colonized, being occupied in year t plus 1. We also estimate an initial occupancy probability, and this being a Markov model, we can derive yearly occupancy estimates or psi from the phi and gamma estimates. Of course, we also want to know how persistence and colonization change between forest types, and we admit that they change in time differently between old growth and secondary forest. The 62 species that we analyze enter the model as random effects in the forest type effect and in the interaction between time and forest type. Because we did this before Rahel Solman's talk on Monday, we also modeled the quadratic effect of Julian Day on detection probability. We fit our model in a Bayesian framework with JAGs using vague priors to the extent that we could. The model converged all right, but I must disclose that the fit was not perfect. When we asked the model for a deterministic prediction of reality and compared that prediction both with our data and with data simulated by the model, the prediction falls substantially closer to the simulated data. Since, however, the prediction is not dreadfully far from our observations, we endure, and I hope that you can endure too. The first result that I want to share is the logit space effect of secondary forest on the time averaged phi and gamma, the probabilities of persistence and colonization. You can see that nearly all 95% credible intervals of these effects overlap 0, but also that they tend to be negative, especially along the gamma dimension. So secondary forest is not improving the persistence or colonization for the vast majority of species. This slide shows sample species-specific results for the rufous, cat, and thrush, a ground-dwelling bird. Filled circles are old growth and empty circles are secondary forest. All plots show temporal variation along the x-axis. On the left, we have the dynamic parameters of persistence and colonization, and on the right, detection probability on top, followed by site occupancy. The gray rectangles show the mean and 95% credible intervals of predicted equilibrium occupancy if persistence and colonization were kept at the average values estimated for the duration of the study. Species does not do well in secondary forest. The golden-headed mannequin, on the other hand, appears to do well in both types of forest, even though for some reason it seems to be increasingly hard to detect towards the end of the study period. Now, moving on to the ideal set of species. The group picture, that is, the parameters derived from the posterior means of the random effect distributions, should clarify my opening comment about unfulfilled expectations. The temporal variation in old growth does not appear smaller than in secondary forest, and there is no suggestion of a buildup of occupancy in the regenerating habitat. The only intriguing temporal sign is, again, the appearance of a slight decline in detection probability through time. In order to better explore the possibility of temporal trends without necessarily building them into the model, we decided to fit a straight line over each of these plots for every iteration of our MCMC chains. And then we look at the resulting distribution of slopes for both types of forest. That's what I show in this slide. So here is a snapshot of the distributions with all plots showing the slope for old growth on the x-axis and the slope for secondary forest on the y-axis. Darker circles mean that more of the slope distribution was away from zero. You can see that for phi, gamma, and psi, slopes appear as likely to fall on the negative as on the positive side of the plots, but for detection probability, circles are clearly concentrated on the negative part of the plot. Is this tendency for decreasing detection an artifact of our analysis? We are not completely sure, but the result was fairly robust to variations in our model. It first appeared with detection varying over time, but not among forest types. Then it appeared with additive effects of time and forest type, then with an interaction between the two, and finally in the model that I presented here with the quadratic effects of Julian day in detection within the year. And this is not all. At some point, we manually checked a few of the automated identifications and found them to be correct. But while listening to recorders, we also found sounds that were very easily identifiable by us, but not picked up by the algorithms. That motivated a look at frequency plots. That motivated a look at frequency plots of the probability that a query sound contained the vocalization of each target species. And here they are. And in a first approach to handle this diversity of distributions, we changed our threshold for accepting an identification to 0.85 and 0.99, as shown there on those lines. And the pattern of decreasing detection probability persisted. So in conclusion, we could not detect a gradual increase in occupancy due to colonization of the secondary forest, but we see a decline in detection probability that is not going away. This decline could, and I emphasize the uncertainty in could, be due to decreasing abundance or decreasing vocal activity in the study species. After attending Alina Lee's plenary yesterday, I realized that we have a bit of data simulation to do here. And we also can try to improve the model fit by inserting some spatial structure in the initial occupancy. Also, in a future paper, we would like to incorporate the uncertainty of the automatic identification output in the detection model. But for now, we believe this result is of sufficient biological concern to be reported. I'd like to thank you all for your attention at this late hour. Thank the meeting organizers and all the people and institutions who contributed to this work, some of which are listed on this slide. Thank you very much.
Any questions?
Thank you, Gonzalo. That was very interesting. Could you imagine that the devices it just got old and the quality of the recordings decreased? I think that happened in another acoustic study.
Our experience with these machines was that when they didn't work, they just stopped recording because of rain. And we had a new batch of recorders used in the last year. So it is a concern, but if anyone has information about gradual decrease of quality in the recorders, please let me know later. And I would like to know more.
Very interesting results.
Thanks.
But have you trained your algorithms on the first year or on all the years? Because if you imagine that it's kind of capturing individuals, but not the species, then individuals slowly replace each other, and then you have the new ones that are not identified. The principle could happen.
That's a good question for which I cannot give a very informative answer now, because it was Ulysses who did the identification part. What I know is that he did a multinomial regression. That's why I talk about probabilities of species being present. And he had a lot of knowledge of the first year data, but still, from my experience in the field, I would be very surprised if the calls changed substantially within 5 years. But I will ask Ulysses and figure out if that's a possibility.
One more question in the back row.
Yeah. Very great talk to get us thinking before dinner. One question I had was whether you considered the potential that local abundances are declining, because we know from, the Royal Nichols model that one covariate that affects detection probability is just the abundance of the animals that you're trying to, in an occupancy framework.
Yes, I do. That's what I try to point that out in the conclusion, but I'm afraid of calling crying wolf before time. But it's very concerning because there's several sources of information saying that the Amazon is drying gradually. Temperatures are increasing. So this could be a small signature of decreasing abundance or vocal activity. But in a way, it looks too smooth to be true. Also, that's why I'm being cautious.
It would be interesting to think about applying the framework that FAR et al. Proposed recently, where you're trying to detect changes in underlying abundance from occupancy data by sort of building on the Royal Nichols work in a multi-species framework. But
that's a good idea. Yeah. I'll look into it. Thank you.
Thank you very much.
You're welcome.
Sadly, that concludes a day of excellent science. Thank you to all the speakers in this session. Thank you to all the students who worked hard to give their first presentation. And thanks to all of you working in English as a second language as well. It's a challenge.
okay, so thank you very much. We meet at 7-ish downtown for the gala dinner. Gala dinner? Yeah, gala dinner. Have some rest. You'll be fed again. And see you in a bit. See you in 2 hours. Là,